thought we'll wait couple of minutes for others to join. And then I remembered that I had this as the last slide in my presentation yesterday, but I didn't show because I stopped since our time was over. So if any of you are interested or if any of your groups are interested, I think you should consider attending this course. So I will cover parts of it today, but this will be a full day course that I will do along with Dr. Nicholas Curry, who did his PhD with us, and then he joined a company in Austria called Tribacher, which makes suspensions for thermal spray. Now he is partly a consultant and partly with a company called MedTech, which makes plasma spray systems. So he has very good experience, and we thought we will do this course together. This date is very special because this happens to be my wedding anniversary. No, jokes apart, this is one day before a national thermal spray conference which is being held in Bhubaneswar on 21st and 22nd. It's not as though you must travel only for this course. There is a national thermal spray conference that happens on 21st and 22nd, right? So if you look up the Indian Thermal Spray Association website, you will see this. Yeah. Who? This conference is at CSIR IMMT in Bhubaneswar. There is another conference on additive at IIT Bombay. That's next month. But this one is in February. So, I think now maybe we should start. Yeah. So based on what I heard from you guys yesterday a little bit, and as I promised, I thought today I will dive into one of the surface engineering technologies, not talk about everything. I gave a general overview yesterday, which hopefully conveyed to you how powerful surface engineering can be, what different kinds of coatings you can deposit, from thin to very thick, from metal to ceramic to intermetallic, everything, right? And then I thought I will today pick thermal spraying as an example. And as you heard, each of those techniques that we spoke about yesterday, whether it's PVD, electrodeposition, even hardening, all of them have many variants within that family, right? So I'm going to take as an example thermal spray and talk about what is new in thermal spray, because I think that is one of the objectives of this course as well, to talk a little bit about fundamentals, to also give you some indication of what the research areas are, which are new, right? So let's start with very fundamentals first, right? So that I don't lose any of you, right? And once you understand what thermal spraying is, then you'll be able to better appreciate what comes next during this 1.5 hours, right? So let's begin by discussing what is thermal spray. Again, let's go to the definition. So as per definition, thermal spray is a process in which surfacing materials are heated to the plastic or molten state inside or outside of the spraying gun or torch, and then propelled onto a prepared surface. Prepared surface is actually surface of the component that you want to coat, right? And the substrate remains cold. It's the material that you are coating which either gets to the molten state or at least to a plastic state, yeah, by the time it deposits, yeah. And to obtain a certain specific property on the surface, you will change this material, of course, right? So if you want insulation, you will use the ceramic. If you want corrosion protection, you can use anything from aluminum to things that are far more complicated. Aluminum to nickel, aluminum to nicrol to nicroly, right? Where Y is yttrium, yeah? So you can make it as complicated as you want, depending upon what kind of performance you desire, right? So, so the specific property that you get from the coating is dependent on the material that you use. There are also various post-treatments, just like in AM, you can do some post-treatment to a coating. You can do some thermal post-treatment to densify. Sometimes you can do mechanical post-treatment if you want the coating to be mirror finished. Yeah, you can do that. Sometimes if you don't like any porosity at all, you can do sealing after the coating is over, right? So many possibilities are there, and we will talk about some of those as we go along, if necessary. Yeah. When it started, thermal spray, it started by accident. There was this gentleman called Max Schupp who was playing around in his lab, and suddenly while he was doing something on his desk, he found metal droplets going and depositing on the wall, yeah, because of some explosive or high velocity gas that he was using. So that was the beginning of the idea of thermal spray. At that time, Max Schupp called it metallization. Even today, some people refer to it as metallization when they are talking about aluminum, zinc, or aluminum arc spray and things like that, right? So it used even lower melting materials like tin and lead, right, to deposit. Now, of course, we have gone way beyond that. So metallization at that time involved atomizing this molten metal and propelling it at high velocity to impact on a surface and form a coating, right? After that, it came to feeding wires or using oxyacetylene torches, etc. But just to let you know that thermal spraying, as per what began as metallization, is almost 100 plus years old now. And because of that history, it has evolved in a big way, right? So this is a very busy slide. I don't want you to read anything. What I want to tell you is, although it started at around 1900 by Max Schupp, today all these boxes are some variations of a thermal spray gun, correct, that is available. So things have changed quite a bit. Yeah, somewhere along the way there was oxyacetylene, then there was plasma, then there was high velocity oxy fuel, then air fuel, then cold spray. So all this is shown in this graph. So let's not get into that for the time being, right? Just be aware that many such things exist which we call process variants within the thermal spray family, right? How versatile is this process? So I told you it's 100 years old. There are many techniques available. How about materials? If you take a catalog now from a supplier that of only thermal spray powder, yeah, again, you can't read, but there is a reason. I don't want you to read, yeah. I only, if I can zoom, I want you to only read this, right? This catalog runs into 43 pages from one supplier. So there are 43 pages of list of powders that you can thermal spray. So you can imagine how versatile this field is. All of these powders written on these 43 pages can be thermally sprayed. Yeah, you see some categories here. Although this is a lousy slide, you can see M. Crowley alloys, you can see metals, alloys, and other composites. You can see carbides. Yeah, you can see many oxide ceramics. All of these can be sprayed, right? So we spoke about how many different process variants are available, and here I am trying to tell you that there is a very large portfolio of feedstock materials. So between them, you can create many kinds of fun coatings in a manner which is completely traditional, right? So let's see how thermal spraying is conventionally practiced. Traditionally, how do people do thermal spray? And then starting with those traditional practices, how crazy guys like us have distorted thermal spray to do something totally different, right? But let's first, to appreciate what we are doing, you must understand what is conventional, right? So the conventional way, one more time, to show it as a cartoon. So you inject the material that you want to coat in a high temperature, high velocity zone. What is the intention? The intention is that this material that you introduce should be molten, yeah, and then the molten droplet should be accelerated, yeah, and accelerated to then go and hit a surface. What happens when a droplet goes and hits a surface? What do you think happens? If there is a molten droplet that goes and hits a surface at high velocity, what do you think happens? Metal pushes out. Any better definition? Molten droplet hitting a substrate at high velocity. What happens? Spreads. Okay. Huh? It splats. Yeah, that is the correct word. Right? A molten droplet comes, hits a surface at high velocity. Yeah, it forms a pancake almost. Right? It splats. Not hard to believe, right? You have a molten droplet comes at high velocity, that droplet spreads. So it forms what is called a splat. Now these splats, if you are moving the gun, for example, these splats can be overlapped. So you can cover large area as you want, as large area as your holding mechanism in your spray booth allows you to vary, right? If you have a robo gun on a robo, it can do whatever is the reach of the robo, correct? So you can cover large areas by overlapping these splats. How do you build thickness? You stack up these splats on top of one another. Yeah, you build thickness. Very simple. This is thermal spray in 30 seconds. You melt material, accelerate, splat to form a dish-shaped splat, overlap splats to cover large area, stack up splats to build thickness. Over, correct? Now you are all thermal spray experts. So let's talk about a couple of things. Why do you want the particle to fully melt? What happens if it does not fully melt? Yeah, suppose it's not a nice droplet. It has a molten skin, but the core is still solid. Imagine. It can happen, right? That your particle is not fully molten. It's partially molten. Then what happens? Okay. What happens? Yeah? It doesn't form a pancake very nicely, right? And it's coming at high velocity, so the middle part which is not molten, it can bounce back, right? Because it's not spreading. Then what happens if it bounces back? That becomes a reason to form porosity in the coating, right? One. And why do you want it at high velocity? Because these are all mechanically anchored coatings, yeah? So before you do this coating, you roughen the substrate by grid blasting, right? So why do you want high velocity? So that these splats, because of the roughness, can stick properly, correct? If it's a very smooth surface, it doesn't stick. If it is not fully molten also, it doesn't stick, correct? So that is the ambition then for a good thermal spray practitioner. Fully molten to avoid porosity, high velocity to get good adhesion. Yeah? That is the mantra all the time. So this is how thermal spray has been practiced for several years. This material, by the way, you can feed it in many different ways. You can feed it as a wire if you want. in certain spray systems. In very rare cases, you can feed it as a rod, but most popularly, you feed it as a powder, correct? Easy to understand, yeah? So when you talk about different variants in the thermal spray family, the real difference comes here. How is this high velocity, high temperature zone created? What is the temperature in that zone? What is the gas velocity in that zone, correct? So all these different plasma, detonation, HVOF, HVAF, cold spray, they differ here. Yeah, this part is the same. This part is almost the same, right? The real difference is coming here, okay? That's important to understand. So a closer look. These particles strike the substrate, hopefully in molten form, right? So if you do it right, these molten droplets will form a splat, yeah? And these splats will stack up to form thickness, yeah? Very simple, looks like. Yeah. So in a way, this splat, I like to call it, splat is a building block for a coating, right? Just like a brick here, right? You can put bricks side by side. Similarly, you can put slats side by side with little overlapping. You can put slats on top of one another. This is the simplest way to visualize a coating. Is everyone with me? Nobody is lost? Nobody is confused? Because if you don't understand this, then next 1.5 hours is a waste. Yeah? So this is important to understand. Yeah? Okay. Good. So same as what we spoke yesterday, if I pick the right material, yeah, I can achieve any function from thermal spray, right? I can get corrosion resistance. In the simplest case, people spray bridges now in the US with thermal spray, only do aluminum or aluminum zinc, right? So you can get corrosion resistance. You can get very aggressive corrosion resistance in a land-based gas turbine where you won't use aluminum or zinc, you'll use something far more complicated, correct? But you can get corrosion resistance. We already spoke about zirconia yesterday, I gave that example. So if you want a thermal barrier or insulation, you can do that. You can get electrical conductivity. Copper on aluminum is a very popular application for cold spray, for instance, right? We spoke about abradable coatings. What did we call it yesterday? What was this called? Clearance control coatings, yeah? Or sacrificial, yeah? So it was that category. You can get other textured surfaces. We also spoke about implants and prosthetic joints, right? So by using the right powder, you can get all these functions by thermal spraying, and that's what makes it very, very useful. Yeah. So advantages, these are clear to see. I've already spoken about that. Many materials, list running into tens of pages, can be sprayed. There is no great heat input to the substrate unless you do this process in a very bad way. Your substrate doesn't get heated. Why? Because you have one droplet coming and immediately cooling. It is impacting a large substrate. The substrate itself serves as a heat sink. Yeah. So there is no reason for any heat up on the substrate. Yeah. If the part is very small, let's say I'm coating this part. Many times you have to do things like that. And then I'm not coating, I'm not doing that, right? Otherwise, if I do like that, then if a particle hits here, by the time I go there, this has already cooled, right? Then I come back. But imagine this is what I'm coating, yeah? Then it's almost always on the part, right? Doesn't have time to cool sometimes, right? Then there is a chance that it will get heated up. And then in such cases, you must make some mechanism for cooling, correct? Which is also possible. So all this can be done. Many times with certain types of guns, you can work on site. You can just put it on a truck, go there, repair and come back, or coat and come back. Yeah. So that is possible, and most of the systems today are automated. Automated to the extent that if a human being is inside the enclosure, the gun doesn't even operate. Yeah, you can't even start it. Yeah, so there is that level of automation now for reasons of safety, etc. Yeah, so very sophisticated now. What are the problems? Yeah, we spoke about this little bit. It's a line of sight technique. What does line of sight mean? BTech. Correct. Yeah. Whatever the gun can see, it can quote. Yeah. So for example, if I am doing this, I can't quote here, obviously, right? Are there coating methods that can quote here? Not thermal spray. Are there other methods that can quote here? Yeah. Many can quote, right? Electrodeposition. I just dip it. Yeah. Or PVD, CVD. There are several which can quote, but thermal spray can't do that, right? Because it's line of sight. You need surface preparation. I spoke about grid blasting. Yeah, you have to roughen the surface. What if I am coating something like this and I want a coating only on this side? Yeah, I cannot tolerate any coating here. Yeah, it's a big problem for me if any material deposits here. What do? You have to do masking. Yeah, you have to do masking. Even that has a long history. Earlier people used to do simple tape masking, right? But as a race, human beings are very greedy, right? You want everything better, right? So to get more and more addition strength, we have, I will come to that later, we have come up with thermal spray techniques which are extremely high velocity, more than 1000 meters per second, right? And you are spraying for better tribology where you are spraying very hard materials, right? So imagine very hard materials heating at 1000 meters per second. Yeah, then tape masking doesn't work anymore. What used to work earlier for normal different kinds of coatings suddenly doesn't work because you have come up with harder materials, you have come up with processes that provide much higher velocity, and then that masking doesn't work. So in that case, you have to use metal masking, right? So masking also becomes a big step when you are using techniques like that. Yeah, all these are not really shortcoming, but yeah, you need to know that some of these can be loud. So if you, for example, talk about detonation spray, it's 80 decibels, 80 to 100 decibels. It's like standing underneath an aircraft. Yeah. Engine which is running, it's that loud, and it's also a sensitive process, more sensitive as you start using new feedstock. Yeah, we will talk about that later. Is everyone clear so far? Any confusion? Yeah, does anyone have questions about why you grid blast, why you mask, stuff like that? No? Yeah, very clear? All right. From yesterday, I've been talking about microstructure and the importance of microstructure in AM, in coatings, etc. Let's look at how a thermal spray microstructure looks like, right? It looks lousy, to be honest. It looks terrible. If you look at thermal spray, inherently it's a defect-prone microstructure. It's prone to all sorts of defects. Let's see what kinds of defects exist. Yeah, porosity. No matter what you do, some porosity will be there. Correct? Arising as these flats stack up. Some powders, you always have a particle size range. Some particles melt, or many melt, and some do not. Right? So there are reasons why you get porosity. Sometimes you get oxides. When you are spraying oxide materials, that's not a problem. But when you are spraying metallic materials, because of the high heat input, some oxidation can take place. And your application then decides whether a certain level of oxide content in the coating is acceptable or not acceptable, right? But oxide content is another important characteristic. People at least the industrial users always question about addition. So if you run a thermal spray job shop, a user will come and ask you, what is the addition strength, or also called bond strength? What is the bond strength of the coating? Why they ask that, even they don't know most of the time, but they ask, what is the bond strength? So you should know how to calculate bond strength or determine bond strength. And just like which AM process has most residual stress? Go back to yesterday or day before yesterday. Huh? Wire arc has residual stress. SLM has residual stress. So similarly, thermal spray coatings also have residual stress, right? So some of these are very typical characteristics of a sprayed microstructure. Remember, we are right now talking about conventional thermal spray. Some microstructures I show here. These are plasma sprayed zirconia thermal barrier coating. Fair bit of porosity, but porosity is good in a thermal barrier coating. Why is it good? There are a couple of reasons why it is good. I would like to hear at least one. Why is porosity good or okay in a thermal barrier coating? Reduce the heat? Yeah, it kind of reduces the thermal conductivity of the coating, which is what you want if you are putting on an insulating coating. What's the other reason? Imagine a thermal barrier coating which was fully dense, no porosity, no nothing. Would it survive? No, it will not survive because of thermal stresses, right? There is no way to accommodate thermal stresses if it's fully dense, correct? That it will bond. Here the bonding will be good, but if there is no porosity, yeah, there is no way to accommodate thermal stresses. Imagine that you are a coating in an aircraft, and the aircraft is taking off and landing. So what does it do? It's basically heating up and cooling, and that induces thermal stresses. How will the coating accommodate stresses if there is no porosity, right? Then it will immediately fail here because of the stresses. So we asked yesterday if porosity is good or bad, and we decided it depends. Yeah, so it's part of that, correct? So it depends. In some cases, this is all right. In other cases, if I'm looking at a wear coating, even this kind of porosity is not all right, correct? All right. So let's come back to this, the same schematic in a slightly different way. Yeah, material feedstock, spray process. I said this is where the difference lies. Yeah, how is the high temperature, high velocity zone created? There are typically three ways in which you create. Sometimes it can be electrical. Electrical meaning you just strike an arc. Yeah, you immediately create a high temperature zone. Yeah, if you have two wires striking an arc, then you create a high temperature zone, and those wires themselves serve as material. Yeah, and these if you have a carrier gas, they take away droplets from that and form a coating. In some cases it is by combustion, this high temperature, high velocity zone, that is most common. Yeah, the simplest form is oxyacetylene flame, but yeah, now you use, depending upon which part of the world you are in, you can use propane, propylene, that kind of stuff. Yeah. In yet other cases there is no flame at all, it is just kinetic energy. We will talk about that a little bit. But what I actually wanted to talk about here is, what is critical is gas temperature and gas velocity in this region. What is also critical is, from this point on, let's assume that we are using powder, right? What is also important is powder particle size, right? Because both of these together will decide how fast the particle gets heated up, whether it melts or it doesn't melt. It will also decide how quickly the particle accelerates, and therefore at what velocity it will go and hit the surface. Is that clear? Yeah. So So these two, as you can imagine, are the most important governing factors in deciding what happens to the particle before it goes and hits the substrate, right? So when you're optimizing parameters, you're usually playing around with this or with this, correct? Yeah. Yeah. So we quickly spoke about electric methods, combustion methods, and kinetic. If you break that down further, I spoke about wire arc. The other is plasma spray. Yeah. What is plasma? Can anyone define a plasma for me? Anybody? I'll give you a hint. It's also called the fourth state of matter. Yeah. What are the three states of matter? That you know. First, let's start with that. Solid, liquid, gas. Correct. 100 out of 100. Yeah. Fourth state of matter. Partially ionized gas. That's apparently the fourth state of matter. So you are working with an equipment that ionizes gas and utilizes all the energy that's available there, thermal energy, to melt and accelerate the powders. The other technique, as I was talking about, is combustion. The oldest is oxyacetylene combustion. We spoke about that a little bit yesterday. Yeah, but now there are many more advancements in that. You have new gun designs which still rely on combustion but enable extremely high velocity in the gun. So high that you get shock diamonds. If you look at the flame, you see shock diamonds. When do you see shock diamonds in a flame? Anyone know? When do you see shock diamonds in a flame? Anybody? When the velocity is supersonic. Yeah, that's when you begin to see, even with your naked eye, you see shock diamonds, correct? So you now have spray systems where you rely on combustion, use oxygen and propylene, for example, but enable extremely high velocity that gives you shock diamonds, right? Now, I spoke about greed. We are greedy. Even that is not okay for us. We want still higher velocity. So people started using air instead of oxygen. Yeah. So if you want to do full combustion, you have fuel, you have oxygen, it combusts, right? What do you think is the advantage of using air? What happens if you use air instead of oxygen? Just think. What happens if you use air instead of oxygen? Why would people want to use air? No other type of gases, nothing. You still need oxygen for combustion. Why do you use air? Yeah? Imagine that you needed X liters of oxygen for full combustion of a fuel. Yeah? X liters of oxygen. How many liters of air would you need? Roughly. How much? If I needed X liters of oxygen for full combustion, for the same combustion, how many liters of air will you need? If it is X, you tell me 0.2X or 2X or 3X. How many X will you need? You'll need almost 5X, right? Because 20% is oxygen, 80% is nitrogen in air, correct? So you'll need 5X air, correct, for full combustion. Now if you provide 5X air, what will it do? It will further give acceleration. You are introducing even more gas, right? So your velocities become higher and your flame becomes cooler, right? Because there is so much non-combustible nitrogen that is available, yeah? So you're getting much higher velocity but much cooler flame, correct? So that is why our greed has taken us to HVAF and you get beautiful coatings because of that. We'll talk about that a little bit. And the third is something called cold gas dynamic spray. To me, all of these are additive manufacturing, to be honest, right? But people now consider this as a big part of additive manufacturing, yeah, for repair, etc. Cold spray or cold gas dynamic spray, depending upon who you are talking to. Uh, the, uh, the terminology is little different, but they are the same, cold spray or cold gas dynamic spray. So how do they compare? As I said, the most important thing for you to consider is temperature and velocity. So let's map all these processes that I showed on this slide on this map, right? Let's plot temperature versus velocity, right? So you have plasma, which is the big daddy. People thought all thermal spray problems were over when plasma spray first came into being because of this kind of temperature. Imagine almost 15,000 degrees is the temperature that you get, right? So people thought all problems over, you can melt anything that you introduce under the sun as long as you do not sublime. It shouldn't be a material which sublimes. All of you know what sublimation is? Silent to direct vapor. Yeah, as long as that doesn't happen, you can melt anything in a plasma spray. Yeah, so this gives you the highest temperature, and we spoke about cold spray. It gives you lowest temperature because there is no thermal energy, there is only kinetic energy, correct? So this is the map. So if you want to buy a spray system, it's important for you to think about this map. What am I going to spray? What temperature does it need? What is the application? So this map is very useful for you to understand what is going on, correct? Yeah, we'll come back to this if necessary, but these are what are most popular today. If you go and look at thermal spray literature or thermal spray market, among the oldest simple flame spray, you have oxygen, you have acetylene, you use a normal lighter, it lights a flame. Your powder is in this canister, you feed the powder into the flame and you're all set, right? The flame will melt this powder and then everything that I said just now will happen. Then some people started into the same flame feeding wire. So you have a wire spool here, feed wire, wire comes out here. Same thing happens otherwise, just like with the powder. Then people started using arc. So 2-wire arc, yeah, strike an arc, have a carrier gas. The wires melt at this tip and the carrier gas carries the droplet to form a coating. Yeah. So now you understand the mechanism, right? What you are trying to do, you understand, right? And then plasma, of course, detonation, again relies on the principle of combustion, but you have a high pressure chamber which is pulsed. So it's like if you go to ARCI sometime, it is like shooting, tuck, 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 you will hear that sound, yeah? And that is determined by what is the frequency at which you allow it to pulse, right? It can go up to 8 hertz frequency, which means it will pop 8 times a second, right? And each time there is a detonation, you will inject powder and that will get melted and accelerated, right? HVOF, say almost similar principle as this, but this gun is modified so that it can deliver very high velocity, yeah, of both fuel and oxygen, and therefore you get very high velocity. This is what I told you. This is a picture from my lab. Yeah, here instead of oxygen you are using air now for the reasons that I just mentioned. Much higher velocity, cooler flame, right? And then this is cold spray. This is a picture from ARCI, but you have many variants of cold spray. Let's talk about cold spray a little bit, right? I told you there is no thermal energy, yeah, only kinetic energy. So what does it do? If you are using kinetic energy and you think back about what I said, how coating forms, yeah, a droplet or a particle comes, hits the substrate, spreads out, forms a splat, forms a coating. So if it is cold spray, no thermal energy, how does a coating form? Anyone? Anybody? How does a coating form in case of cold spray? Gravity. So in the definition you said uh, particles which are plastic or molten, right? In this case the coating forms by plastic deformation, not melting. How many of you have heard of plastic deformation in the first place? Yeah, some of you have heard plastic deformation. So therefore automatically, huh? Why are you adding permanent unnecessarily? Yeah, just say yeah, plastic deformation. Okay. So what does it mean? If you have some ceramic, can you deposit by cold spray? You can deposit by cold spray because it won't plastically deform. So that becomes an additional limitation of this process, that you can only deposit materials which can plastically deform, right? Like most of the metals do, right? Aluminum can plastically deform. Zinc, all these things can plastically deform. Ceramics don't, right? So that automatically imposes a limit on what you can spray and what you cannot spray, all right? So that's important to understand. So let's talk a little bit about what is new in thermal spray. Let's talk about three things. Let's shortly discuss three things. What's new in equipment for thermal spray? What are the advances in feedstock? Maybe I'll spend most of my time talking about this, and also with processing, right? Moving forward. But all of you are clear about what is present day thermal spray, right? Conventional. Now you're clear, right? Let's talk about equipment and feedstock development, because that really sets the tone or lays the foundation for what comes new or next in thermal spray, all right? Let's look at some advances in thermal spray equipment. One of the recent things is called a new gun from Saint-Gobain, which allows use of a flexi cord, right? Just as we spoke a little bit about limitations of cold spray, where we said only materials that can plastically deform can be coated. What is the disadvantage of arc spray, wire arc? What do you think? Yeah, two wires forming an arc, and then that material being carried away by a carrier gas. What's the limitation of that process? That your feedstock has to be conducting. It should strike an arc, correct? If it doesn't strike an arc, that process doesn't work, correct? So in FlexiCord now, yeah, people do many fun things. The exterior is conducting and it could have ceramic packed inside, right? So it's a flexible cord. There is a way to strike an arc, but there are all sorts of materials inside the cord, right? So that's a big advantage. It's also useful that you can inject that flexi cord through the center of the gun, right? And today you get these kind of flexi cords or wires in many different diameters, in many different chemistries, just like powder. Otherwise, the ability of a material to be drawn into a wire was a constraint when you wanted to do wire arc spraying. So you're removing that constraint in a sense. Yeah. This is a high velocity air fuel system from my lab. Looks very nice, doesn't it? Right? Very stable flame. Yeah. We use this mostly to spray tungsten carbide, and this will give you an idea of how high the productivity is. Beautiful flame. We put on almost 10 to 20 microns per pass. Every time that goes around, you build 20 microns, so it's pretty quick. Yeah, in about 10 rotations, you build 200 microns on whatever part. So that's a big advancement. I spoke about it a little bit, but very quickly, let's compare HVAF, which is new, with high velocity oxy-fuel, which is old, right? And see what are the differences. The main difference is that you use air instead of oxygen, right? Compressed air instead of oxygen. We also spoke about what that leads to. It leads to much higher gas velocity because you are using 5 times as much gas as you would if you used oxygen, and therefore it lowers the flame. Why is this interesting, right? Why are both of these interesting? Lowering the flame means that there is no thermal damage to feedstock. We spoke about what different defects can be present in a thermally sprayed coating. One of them was oxidation. Yeah, you could say that in some cases there is also elemental depletion. None of that happens if the flame is little bit colder, right? And second, of course, is higher velocity where you get extremely good addition. So today, if we do an addition test, there is, by the way, an ASTM standard C633-79. What do? You almost exactly this size. You coat a 1-inch button, right? And then glue it to another 1-inch button, right? And try and pull it apart in a UTM, right? And the force at which you pull it apart is the bond strength or adhesion strength of the coating, right? That's how it's done. So when we do HVAF, we always get failure in the glue. We never get, because there's no glue hard enough to kind of overcome that bond strength. So we have come up with new ways of testing, like brazing or something like that, to be able to do that test. Yeah, so it gives you excellent adhesion, almost no porosity and things like that. We also have a handheld version of this gun available now, right? So that we can, we have actually taken this gun to a boiler, gone inside, sprayed it and come back, yeah? And many of the boilers in Sweden operate on waste material, so therefore they are prone to corrosion a lot, and therefore they need protection when they use that kind of starting material in their boilers, and this is a good way for us to go in there and protect those boiler tubes. Yeah. The other thing that is new in the thermal spray world is the availability of axial feed capable plasma spray torches. Historically, this has been the holy grail for thermal spray practitioners. You could never inject the material through the center, right? You always injected it radially outside in the plasma flame, right? Two things happened because of that. One is you could not utilize all the energy that was available in the plasma because it didn't come right from the center, yeah? So you wasted a lot of thermal energy that was available. The other is if you introduce it radially, the powder behaves in a very different way. It behaves crazy. If your powder particle size is fine, it just doesn't go in the center. It bounces off. Because at that temperature, what's the plasma temperature? I showed you. How high is the temperature? 15,000 degrees, right? So at that temperature, the gas is very viscous. The viscosity of the plasma plume is huge. Yeah. So if you have fine particles, they cannot penetrate the plume because of the viscosity. To overcome that, if you increase the carrier gas flow rate, some of the heavier particles just because of density go right through, right? So you then need a very precise window for the right kind of particles to go through the center, right? Instead of that, if you can inject it axially, like here, then everything works well. Your thermal energy is used up fully, your particles travel in a manner that you would want them to travel, and that leads directly to higher deposition efficiency, right? So this is also something which is very new in plasma spraying, yeah? I'm showing the same problem in a magnified sort of way, yeah? So there is segregation of powders that happens. You need higher carrier gas flow if these kind of particles need to come through the center, right? And then beyond a certain particle size, you cannot do anything. they just bounce off, right? So that's the problem with radial injection, which is then solved if you manage to feed it axially, right? Uh, that's not so important. Let's talk about feedstock. We spoke about equipment. Let's talk about feedstock. What is new feedstock available? Yeah. So today we can spray all this entire family of materials: metals and alloys, ceramics, cermets, even polymers. I showed you one picture about cookware, frying pans. People do that by thermal spray as well. Yeah. And we have now graduated to look at many new classes of materials. We already have few publications on all of these things: high entropy alloys, graphene, carbon nanotubes inside the coating. So these were not traditionally materials that one would thermal spray, but we are able to do all of these today in thermal spraying, and that just expands this window of what you can do and what you cannot do, right? To give you a better example, we are a very small group, yeah, extremely small, and these are all the materials that we actually have sprayed in our lab. Just imagine, right? All sorts of nickel-based superalloys, 625, 718, CMSX4, all of these are mostly for repair applications, right? If you want to repair an existing superalloy component, we can spray all of these materials, right? A range of M-Crawleys, all of these are bond coats for TBCs, right? Some are pretty simple. We use these kind of things for instance, boiler applications that I mentioned, yeah? And these more complex bond coats we use for gas turbines, right? We have sprayed a range of cobalt-based alloys, titanium also again for repair. Look at oxides, we do all sorts of stuff. If time permits at the end, I'm going to talk a little bit about battery materials, right? Very complicated materials, but we are able to spray these as well, yeah? My dream at the moment is to combine solid lubricants with a wear-resistant material, and that's why we have been working on graphene, tungsten disulfide, also hexagonal boron nitride. We are also looking at hard materials such as diamond and cubic boron nitride. So this is a range of materials that is sprayed by a single group, yeah? I'm not putting this up to show off, but I'm putting this up to let you know that your imagination is the limit. If you use the right material and the right process, you can do almost anything, right? Powders, with AM, we were talking about, oh, you must use gas atomized powders. They should be perfectly spherical, otherwise you can't feed them, yeah? I've just picked out some powders that we use in our lab in thermal spray. All of these can be fed. All of these get fed nicely, and they form good coatings. So no problem. Yeah, you don't really need to have spherical powders, right? It can be angular, it can be agglomerated and sintered, it can be sintered and crushed, anything, yeah? It works well, as long as you know what is happening and what you want to achieve in the end, right? If you know, then you can get there. I want to talk, despite all these different feedstock that is available, I want to talk a little bit about some opportunities and compulsions that drive you towards looking at new feedstock. Because one of the things we wanted to deal with during valedictory function is new areas of research. So I want to cover some of that part here just now, right? So let's talk about opportunities for a new feedstock that synchronizes with new equipment that is now becoming available, yeah? Then these also make for very good research topics if some of you faculty are going to apply for grants, right? And then we began by talking about sustainability, right? There are some kind of materials which have been used by industry for many, many years, but now we are raising questions about use of those same materials, right? So you want to find appropriate replacements for those materials which are used currently in very large volumes, right? So you want to look at replacement for that, yeah? So these are some of the new developments. One is availability of rods of different composition, not very new, but this synchronizes well with new equipment that allows rods to be fed, yeah? We are very excited about this FlexiCord because just 2 weeks back on my way to India, Saint-Gobain, they launched something called cord plasma spray, and that's a result of all the work that we have done in our lab with their FlexiCords. So it's the first time that we have shown that even using a cord like this with zirconia, you can get columnar structure, right? So that's a big thing right now. For us to be able to get columnar structure with a cord like this, nobody's shown that before, right? So this is something that is happening because of the new axial feed plasma torch that is available, right? So you must exploit new equipment by coming up with new feedstock, and that combination can give you a lot of advantages. Let's talk about sustainability a little bit, right? Because that's the central theme of this course, right? If you look at tribology and wear coatings, and I'm happy if someone wants to argue with me about that, the only material that comes to mind is tungsten carbide, yeah? For any thermal spray coating industrially used, what comes to mind is tungsten carbide. Chrome carbide comes a distant second. When do you think of chrome carbide? When you're thinking about higher temperature application, because tungsten carbide can be used only till about 500 degrees or something like that. So beyond that, you cannot use that, right? So if you're looking at higher temperature wear, you consider chrome carbide, otherwise not, yeah? The first use of tungsten carbide was way back in 1942, right? Almost 80 years ago, people started using tungsten carbide. So not much has changed, yeah? And if I'm a researcher, I'm depressed to see that if I'm looking at wear coatings, nothing has changed for last 70, 80 years, right? It's not good. There should be something new happening, correct? Let's look at other problems with tungsten and cobalt, right? Both of them are fairly high on what is called the critical raw materials list in EU. We spoke a little bit about that. 50%, more than 50% of tungsten comes from China, and that's not nice, right? If you look at cobalt, it's even worse. Almost 70% of cobalt comes from a tiny African country called Congo, and this is bad situation to be in, correct? On top of that, cobalt is also, it has all sorts of health issues associated with that. So you don't like cobalt, you don't like tungsten either, but tungsten carbide cobalt is used in large tonnages by the industry today, yeah, to solve their problems of wear, right? So we in our group have been looking at, can we first of all eliminate or minimize cobalt? First question. Second, can we also replace both cobalt as well as tungsten carbide? For me, this is a relatively low-hanging fruit, because in my mind, I can think of many ways of replacing cobalt. This is much, much harder, because this is a big daddy material. It's very hard to replace tungsten carbide, right? So a lot of our work in the last 3 years has been focused on trying to minimize or eliminate use of cobalt, right? For example, we've been looking at what look like complicated chemistries, but they're not actually, right? We work on this with Höganäs, and they have for us made all these different kinds of formulations. The nice thing is, with all of these alternative binders, we get outstanding coatings, right? Same percentage of binder, but the binder chemistry is different. Some of it is completely cobalt free, right? These two, for example, we get excellent coating. So that was step one, right? We have investigated it to death almost. This little complicated slide, but if you look at summary, depending upon what kind of surface degradation you are talking about, yeah, so some of these are even better than the tungsten carbide cobalt chrome, which is the reference material. In some cases, they are almost as good. Are you guys playing tic-tac-toe? Then you can put it up on the screen. Yeah, let's all play for a while. Yeah, because I've been through that phase. It's good to play tic-tac-toe sometimes. It's nice. Yeah. But this is a summary. It's a great way to get rid of cobalt. Yeah, there are good ways to do that. What about tungsten carbide? Yeah, if I look at tungsten carbide on the Mohs scale or the hardness scale, I find there are many materials above tungsten carbide. Correct? All of these, for example. Why can't we spray those? Correct? Why are we stuck with tungsten carbide? Because all of these are conventionally very hard to spray. Yeah, they tend to degrade thermally much faster than tungsten carbide. Correct? So we've been looking at, for instance, titanium carbide as an alternative. It has all the good attributes that you would want in a wear-resistant coating. The challenge is, how do you retain TIC as TIC? You start with TIC, but after you spray, how do you get TIC in the coating, right? But we've been looking at different ways. Why is TIC exciting? Because it has no problems that tungsten has in terms of availability worldwide. Yeah, a lot of titanium available everywhere, including in India. India is a pretty large producer of titanium, actually, right? So we have looked at titanium carbide by a couple of prominent techniques here, and we always get a performance which is kind of halfway between the two popular materials that I showed for wear, tungsten carbide and chrome carbide. It's somewhere in between. Yeah, and there are a lot of results out there which consistently show the same outcome. Yeah, titanium carbide is very nice and gives you something in between those two. Yeah, a couple of years ago, actually during COVID, we started an interaction with Hyperion. It used to be part of Sandvik, but they have become separate now. And they are a company that makes grinding media actually, right? They don't make, they have nothing to do with thermal spray, right? So I gave a talk at Hyperion when everybody was sitting at home, including me. Their scientists were sitting at home. And one of my students is in charge, old master students. He's in charge at Hyperion. So one day he called me and said, everyone sitting at home, I want to expose them to new fields. Can you give a talk while you are sitting at home? I said, no problem, but I don't see any connect. He says, doesn't matter, let's do something. So I gave a talk to Hyperion. And I knew at the end someone will ask me, so what are the opportunities to collaborate, right? So I did some reading on their website. So as I expected, I was asked that question and I said, honestly, I don't see any way to collaborate because you work on grinding media, I work on thermal spray. I don't see much common ground there, but I am very surprised to see some of the grinding media you make. What is their grinding media? Their grinding media is diamond and cubic boron nitride, and they cap their diamond and cubic boron nitride with nickel by electrodeposition. Yeah, so very interesting way of making grinding media. Then they sell it as powder, or they somehow anchor it on grinding wheels. Yeah, but that's what they do. So I said, if you, I won't pay for it, but if you give it to me for free, I would love to spray these nickel-capped CBN and nickel-capped diamond. So that's how it started. We got some powder from them. This is nickel-capped diamond. We did some SEM. So each diamond particle then is coated with nickel phosphorus, right? It's cladded like that. And we sprayed that. Amazing, right? When you looked at microstructure, I wasn't sure if we would get a coating, but we did. Two things happened. One is we lost a lot of diamond, right? We could retain only 15% of the diamond. The second thing was all the diamond which was retained was much finer than what we started. So there was fragmentation of diamond, right? So those are still problems, but we found outstanding wear properties, right? We couldn't even see a wear track when we did wear test. It was that good, yeah? So we find this extremely promising. That has been the subject of a couple of our recent papers on thermally sprayed nickel capped diamond, very nice. And because of that, we also got encouraged to look at cubic boron nitride. We have kind of done the same. Again, pretty nice properties, right? 10 to the minus 8, 10 to the minus 7 specific wear rate. So this is also something we have published. But the next step for us is silicon carbide, because this is cheap. I don't mind losing 80% silicon carbide when I'm spraying. I don't want to lose 80% diamond or CBN, but silicon carbide I don't mind losing. So this is something we have started doing. Had them try and coat nickel phosphorus on SiC. They are not so successful, but the coatings are not bad, and so this is something that's in progress. So I think this is a good track for research, right? Finding new materials for wear, right? Which don't rely on scarce materials like cobalt and tungsten. How about liquid feedstock? I want to, so how much time do I have? 11 o'clock? Yeah? Okay. So I want to talk a little bit about liquid feedstock, right? How many of you have heard of liquid being used in thermal spray? Nobody, right? Yeah, that's why I'm talking about it. Let's talk about using liquid in thermal spray. What is the context? Why would you do a crazy thing like this, right? Let's go back to thermal spray and what we want to do. Yeah, you have seen this before. Our idea is to fully melt, to obtain dense coatings. Our idea also is to ensure that you get high velocity to achieve good adhesion. There is a problem here, but if you want high velocity, what does it mean? It means the particle residence time is very low, right? Once you inject and you want it to travel very fast, it has very low residence time. That residence time is of the order of milliseconds, yeah? So all action has to happen in millisecond time, correct? What does that do? It imposes an upper limit on your particle size, correct? So you need to pick your particle size such that in that millisecond time residence time, it will fully melt, correct? So this is easy to imagine, right? For that reason, your particles need to be below a certain size, right? If they are ceramic particles which are high melting, then they have to be finer. You have to be 45 microns or less. Otherwise, they don't melt in that short residence time that is available. If they are metallic particles which have slightly lower melting point, you can go a little bit higher. Maybe you will see particles which are 90 to 100 microns. But more than that, you can't spray. Yeah, I mean, you can't spray in the sense you will not fully melt, correct? So that imposes the upper particle size limit. Do you think there is a lower particle size limit for these spray powders? Is there a lower particle size limit? Yes? Someone said yes? Yeah. Why? Why is there a lower size limit? Coating will not be formed. Evaporate. Yeah. I mean, that's a remote possibility, but they could evaporate. Any other reason for why there is a lower particle size limit for feedstock? The main reason is that it doesn't flow. If your particle size is below a certain size, let's say 3 or 4 microns, it does not flow at all. It is like talcum powder. It sticks to each other, doesn't flow. It clogs in your powder feeder, it clogs in your tube that is carrying the powder. Somewhere it will clog, right? It doesn't flow. That's a big problem. Yeah, so the lower limit is governed by flowability. But if you had a wish list, would you like to spray a fine powder? You would, right? Because that is the way you get a refined microstructure. That's the reason why people get into nanomaterials and things like that, correct? So if I had a way, I would like to spray very fine powders, maybe sub-micron powder also, but for the longest time, we could not do it in thermal spray. So that is the motivation for liquid feedstock. Yeah, you want to overcome these feeding problems, correct? So two ways. One is put this fine powder, sub-micron or whatever, into a suspension. Put it in water, put it in alcohol, then suddenly it doesn't matter. Yeah, you can feed it like a liquid, correct? No problem. If you want to make life more miserable for yourself, you can forget this powder. You can use something called a solution precursor and hope that these particles will form during that millisecond time, and then those particles that are formed will serve as feedstock, right? So this is something very new that we have been trying. Let's talk about suspension a little bit. What happens if I use a liquid feedstock? These are the kind of pancakes or splats you will get. This is a slightly poor micrograph, but this has come from a single particle, from powder, right? About 100 microns. If you see this scale bar, about 100 microns. If I look at a pancake that comes from a solution, it's 1 to 2 microns, right? So I'm getting a splat size which is 2 orders of magnitude finer. And as a researcher, that is very exciting, right? You're able to refine your building block now, your small building blocks. So it has a lot more flexibility to accomplish whatever you want, right? Many people say, is this complicated, using liquid feedstock? In my opinion, not at all. Yeah, so this is conventional thermal spray. In this case, I am showing plasma. You have a powder feeder. Only thing you do is get rid of this powder feeder and have a liquid delivery device. Yeah, so it's simple. That's what I like about it the most. That it uses all conventional thermal spray hardware, yeah, and therefore it's easy to adopt. Once people understand what benefits it can offer, it's easy to adopt by existing users. You just need a different feeder, that's all. Yeah, everything else is the same. I don't want to get into so much detail here, yeah, but I did mention suspension and solution precursor. If you use a solution precursor, then you don't have the powder already in solution. Yeah, you need some reaction to happen, right, before a powder is formed. So this is even more complicated compared to using a suspension, right? And all of these, having a solvent or having all these additional steps happen, require additional thermal energy beyond what you need for melting, right? So if you look at literature today, you will mostly see these terms used. Suspension plasma spray. You will not see suspension HVOF spray or something like that. I mean, you will see some literature, but not so much. Same with solution precursor. Solution precursor plasma spray, right? That is because plasma is ideally suited to provide the thermal energy that all these reactions need, right? On top of that, now you are able to feed this feedstock axially through the center, right? So people who were disappointed or unsuccessful with using liquid feedstock earlier, now suddenly can consider going back to liquid feedstock and get some very interesting results, right? And I will show you some of those. So while I was at ARCI, this was work by my first PhD student, right? We have already shown that even though this may be a very complicated looking process, if you do it right, you can actually form in flight these kind of particles, yeah, which can then become feedstock for coating, right? And with some careful process evaluation, we could show that if you don't do it right, you get all lousy stuff. If you do it right, you begin to get these kind of particles, which are few hundred nanometers, but certainly sub-micron, and that is ideal, correct? That is what you want to see, right? And similarly, if you do it right, you get junk on the substrate, but otherwise, if the stars are aligned and you have prayed hard enough, yeah, you get nice pancakes that can lead to formation of coating, right? So that was the beginning, and now we have used the same thing which we had learned from radial feeding and extended it to axial feeding now. So we are able to get very dense SPPS coatings, and so I want to make this point clear. If you use a suspension, all these additional steps are not necessary. If you use a solution precursor, you have these additional steps before powder is formed, and then rest of the process is the same, right? Is that clear? A little bit? Yeah. Why are some groups crazy about using suspensions? They're crazy because it was soon found that you could get columnar coatings like this if you used submicron particles in a suspension. Yeah, this is the main driver. Yeah, it's not exactly like a EBPVD columnar coating, but it's close. It gives the same effect. What is that effect? Yeah, it gives you the strain tolerance because it has this finger-like structure. So when you have heating and cooling, it can expand and contract and therefore accommodate stresses, correct? That is very crucial in a thermal barrier coating, which sees thermal cycling. You want this to happen, right? One more time, if it was dense, it would delaminate there in no time. Yeah, if it's columnar, it goes on forever. That's what you want, right? So now, today we are able to get not just columns, but we are able to also design columns. We are able to get, we are able to decide what kind of column density we want. How many columns per millimeter? That also we can decide, right? So we've advanced a long way. We can play around even more, right? So we now know exactly what happens, right? If the particle goes like that, it doesn't form a column. If the particle goes like that, it forms a column, right? And the particle will go like that only when it is fine and doesn't have enough momentum. It goes with the gas flow, right? Close to the substrate. If it is larger and has enough momentum, it just goes straight and doesn't form columns, right? So we understand this very well now, and we know when columns form. We also know when columns don't form, right? And this kind of understanding for any process is crucial. Same with AM, and that's why I was emphasizing that you must look at evolution of microstructure. What happens at the beginning? What happens with little more time? What happens? I mean, does it stay columnar, or is it going from columnar to equiaxed in case of AM? In this case, how do columns grow, and in what circumstances do columns not go? Yeah. So this cartoon, without again getting into details, this uses ethanol as a solvent. If we use water or an ethanol water mixture, we don't get columns, and that's because when we are using this, the droplets are larger and then they go like that, and therefore not form columns. Yeah. When we use ethanol, because of the right kind of surface tension, etc., we get smaller droplets which travel like that and form columns, right? So if you're doing research, you need to get deeper and understand this. For us, this has been very useful for a couple of reasons. Because we know what is happening, we have been able to dispel many ghosts which existed about using liquid feedstock, because most people we spoke to say, liquid feedstock doesn't work. It doesn't give us good deposition. Yeah? Deposition efficiency is very poor. Yeah? But now all that has changed. right? We now, even 5 years ago, what used to take us 4 hours and use 12 liters of suspension, today we can do it in 12 minutes and use 1.5 liter of suspension. What does that do? It moves this from being exciting to an academic, because it will get nice papers, to becoming exciting on the shop floor, right? And that should always be our effort, that what we do in the lab should be exciting for the industry as a user, right? So suddenly we are in a domain now where all sorts of guys, including Pratt and Whitney, are after our small group in Sweden to help them get coatings like these, right? So that should be our effort at all times. The nice thing about us investing time in understanding how columns form was also the fact that we understood how to avoid forming columns, right? From the same understanding, now we know how to avoid forming columns. And that is important when you are looking at functions other than TBCs, right? Because we already said that do you want defects, do you want ports, depends, right? For TBCs it's nice, for wear it is not nice, right? So now we know how to avoid defects in SPS, and therefore even if we start in a lousy way, this was our very first trial with suspension chrome oxide. If you know, chrome oxide has many large applications, including in Anilox rolls. How many of you have heard of an Anilox roll? Anybody has heard of an Anilox roll? It's used in printing. Yeah, so typically it is chrome oxide coated and then laser engraved, right? So that's a typical method of making these Anilox rolls. So we started with chrome oxide, horrible coatings. If you see here, there is a tendency to form column. This is called a column head, yeah. But we don't want columns for chrome oxide, yeah. And because we understand the process much better now, we can go there very easily. This is suspension sprayed chrome oxide. So imagine columnar coating on one hand, imagine such a dense coating on the other, right? So we have great microstructure control, yeah, using liquid feedstock, yeah. And I think that has allowed us to do many more things. Right. Something else that is new is we have started using filaments or these flexi cords that we spoke about and trying to feed that into our axial plasma spray. We have learned many new things with that. It is very stable. It gives you a lot more choices. In a sense, it uses a polymer when you make this flexi cord, and that polymer in a loose sense works as a solvent, right? It is holding the powder particles together, and just like you want the solvent to evaporate immediately when you put it into a flame, you can have the polymer immediately evaporate, right? I think I'll stop here. It gets a little more complicated from this point on, but we have also been looking at, now we can spray with powder. That is, we have done that for donkey's years. We know how to use liquid. So can you use powder and liquid together? I mean, some of our recent projects have focused on using these together. And that is a pathway that we want to use now to combine, for example, a wear-resistant coating with a solid lubricant, right? So this is what we are looking at. This is a picture of both of them being fed together. Yeah, we are feeding powder through there and a liquid from the side, and works very well, right? And we have got some very nice microstructures. This is what we want: a large splat coming from the powder, a fine splat coming from the liquid, right? And this gives a good way for us to construct all sorts of composite coatings. One of the things that we've been very proud of is our ability to incorporate graphene. Yeah, many times when groups work with graphene, they go hunting for a graphene platelet in an SCM or TEM because there is not so much graphene that they can incorporate, right? But they want to show it in a paper, right? So you have to go find a graphene platelet, but that's not how it should be. You should get graphene everywhere, right? That's what we get now, yeah? And for that reason, we get amazing friction coefficient, right? by incorporating graphene in the coatings, right? But that's just an example. Uh, I am going to fast forward because perhaps there is not so much time. Just wanted to show you we going into a boiler with our portable HVAF. Yeah, quite amazing to actually go there and see that happening. Uh, So this is so this part that you see here is inside this boiler. Yeah, this guy setting it up and then eventually spraying. So this has been a very successful. Do you see shock diamonds there? Yeah, did you see shock diamonds just now? Yeah, those are the shock diamonds because this gun is supersonic. Yeah, so. Many other applications we are looking at, SOFC, etc., etc. But yeah, I will end with this. Our recent project is on solid state thin film batteries. We started it just for fun to try and see if we can work with crazy materials like that. Nobody's ever sprayed them before because they are tough to spray. They tend to lose lithium. Lithium is very low melting, so your lithium tends to go off, right? So we started with this. Our ambition was very modest. Just wanted to see if we get any kind of coating at all. So we initially did that, got some coating. The next thing was to see if there is electrochemical activity. Yeah, we got some electrochemical activity which kind of didn't excite me so much because it's a long way to go to make it useful for a battery, but it excited some other groups who saw these results. And because of that, we have got a much larger project now which allows us to not just look at LTO but solid electrolyte, the cathode as well. And then we spoke about greed. I am greedy, right? So now I was trying to see if we can build all these three together, right, to get a half cell or a full cell, and we are able to do that as well, right? But I will stop here. If you have any questions, I can take those. And if you have interest, mark this in your calendar, my anniversary date, yeah, and let's see if you are in Bhubaneswar for this short course that we are doing in tandem with the National Thermal Spray Conference, yeah. Questions? Anything? Tired? Too much information overload? No questions? Nothing? Great. Do you have any announcements to make? There are no questions, looks like.
No question?
Nope.
Then they need to write exams.
Yeah, I must give a quiz in the afternoon.
Yes.
Or tomorrow.
Tomorrow afternoon we'll have a quiz.
Shall we have a quiz tomorrow? People who fail don't get a certificate. Yeah. People who pass will get a certificate. You tell me, please. Try.
Okay.
For you, what is sustainability, first of all? Let's start there, and then we can see how it is relevant or how you can apply. It has or doesn't have that impact? What are you saying? If I am extending life of a component by 2 times, 3 times, 4 times, does it have a sustainability impact or it doesn't have? Yeah. If I am putting on a better thermal barrier coating which allows a gas turbine to operate at temperature which is even 5 degrees higher, does it have sustainability impact or it doesn't have sustainability impact? Repair, all that as well. So, what is laser coating? I want you to make some effort at least, right? Otherwise, you can Google and you will find differences. But tell me, what is laser coating?
Thermal, we can use instead of thermal, whatever energy we are providing through thermal here, why can't we provide through laser? What is the differentiation between thermal spraying and laser coating?
You start, you give me half the answer, I will complete. What is laser coating? Let's start with that.
In terms of we are giving energy to the heat material through lasers.
Yeah.
But here we are giving energy and heat input through some
Correct.
plasma.
So laser coating is, as an example, laser cladding, right? So we spoke about laser cladding yesterday. We spoke about thermal spray. We also spoke about the fact that both of these are oftentimes not competing but complementary, right? So yeah, laser cladding has a role to play. Can you get columnar coatings with laser cladding? You cannot get. Yeah. Can you get 5 mm thick layer by thermal spray? You cannot get. You can get it by laser cladding, right? So each of these has a role, right? And you need to think. I mean, this is something we spoke about yesterday. Now, I can't. We can't say now, oh, why can't we do all this by PVD? You cannot do, because it's a totally different technology, right? But what PVD does, nothing that I spoke about today can do what PVD does. Correct? One more time, most important, these are non-competing technologies, all of them. Yeah. So these kind of questions after what we spoke yesterday should not at all appear. Correct? These are all complementary technologies. Each of them has a very specific role to play in a designer's portfolio, right? So please appreciate that. Any other questions? Or maybe you catch me quietly over tea if you don't want to ask it in open. Yeah. So.
Yeah, okay, we'll have tea break, 15 minutes, then we'll back to the next session of from the hexagon. Okay, Santosh Nagaraj is going to handle the next session. Okay, thank you. We'll verify. Yeah, welcome back to the second session of today's program. Here we are, our new speaker is from the industry from Hexagon, Santosh Nagaraju. Okay, just to brief about his profile, Santosh Nagaraj is a technical specialist at Hexagon, Indo-Pacific region and all. And Dr. Santosh Rajaraju leads the materials and manufacturing solution at Hexagon India. And he started his career from Scientific Farming Technology Corporation, US-based material farming simulation company, where he held various positions like technical support and business development. He also worked as in the SKF bearings in R&D team and all, and the farming and heat treatments and as well as rapid prototyping operations. And currently, Santosh Nagaraj is working in the with MSc Mark software, technical specialist, and as well as BD for Indo-Pacific region. And he has done his master degree from machine design from RV College of Engineering, Bangalore. And Dr. Santosh has credit implementing the various advanced simulations solutions at global OEM and as well as 3D printing services in the R&D institutes, and he played a crucial role in the providing end to the solution for the users in the conventional and as well as in the IT manufacturing process and all. You will deliver more on this the how we can drive the optimization for IT manufacturing, how we can use topology optimization, lattice structures, how we can minimize the weight of the materials, and also you will give the Simofact software how we can make use numerical modeling aspects in terms of IT manufacturing. Okay, with this brief introduction, I welcome you, Dr. Nagar. Please take this.
Okay, so hope I am audible for the people sitting in back. Okay. Good morning, and thank you for giving this opportunity to be part of GAN event. So I will start with my quick introduction. So sir has already introduced. So I have almost like a decade plus experience working on manufacturing. I started my career as a R&D specialist at SKF Bearing. So I started as a material research engineer, then the manufacturing and testing. So since 2018, I am with Hexagon, where I look after software or application of software in the field of manufacturing. So looking at course content, what I have chosen is, I have chosen more of application related. So today my focus would be not much on the technology point of view, but how do we use this technology in the industry? So more of the case study, and how do we get success when we use this set of software tools in the manufacturing. So it's more focused on that, and if you have any question during that, so feel free to ask me. So it can be more interactive. You can just raise your hand and stop me at any point of time. So I represent Hexagon, and I am technical specialist. I look after Indo-Pacific. So and also I will travel a lot, and I will be part of many university programs. So we were in fact do a lot of AM workshops, so where we train the students on how do we start from topology, manufacturing and quality, because Hexagon being one of the company where we have a hardware and software under the same roof. So otherwise in fact we get to see a lot of company who pioneer in the hardware, but couple of people are pioneer in the software, but integration is the key. So that is where the Hexagon stands. So quickly, let me use pointer. So yeah, I'll start with the company introduction. So what we do, then we jump into what is AI driven. What is that AI driven optimization and how it is different than regular optimization, and a couple of customer success stories. End, so feel free to stop me. So this is what before I jump into the optimization. So if I have to implement any component, or if I want to implement a 3D printed or additive manufactured component, all these steps. So either I can start from the point 2, or I can start from the 7. So we call it as, we start as a re-engineering or reverse engineering. So when I say reverse engineering, I have the component, I want to replicate the same with a different technology. In the sense, manufactured component, I will scan it, then I will manufacture with additive or hybrid manufacturing.
So that is a reverse engineering, producing the same component with a different technology, and it has other benefits like investigation of what material used, what kind of coating, and how it is manufactured. So in re-engineering, so we start with the selection of existing component, then we try to optimize something. It might be the lightweighting point of view, it might be from the topology optimization point of view or the performance point of view. So when I say optimization, it cannot be only what we do stress-based optimization using any of the tool. Even we have Apex Generative Designer, Nastron, or any other solution. So it is only stress-based optimization. So optimization cannot be only stress-based. So it has to be from thermal point of view, frequency, and other stuff as well. But we can do that as well. So as I said, before we jump, so there is something called part identification. It is not that every part can be replaced with the 3D printing technology. So now we have to identify the part which is more realistic for a 3D printing. Otherwise, my whole exercise or my whole effort will go wrong. So now in fact we have developed one software for that. So where we upload the component and define this is my component and material. So what it will do, it will search for a similar material available with the 3D printing, because 3D printing has limited material as of now. You take polymer or metal. Let's take example of metal which we have done for one of the university race car recently. So it was printed with aluminum, but in aluminum there are only two grades available for 3D printing. That is of 10 mg and the second is of lower aluminum with some alloy material. So now if I replace the existing material with the 3D printed material, so what will be the difference in material property? So if I come to know that, rest I can easily calculate. If I am reducing my yield, so what will be my fatigue life, or what will be the performance of the 3D printed material? So this is very critical. In fact, we have limited resources or knowledge available on 3D printing. So it is very hard to somebody to directly say yes, this part can be easily replaced with the 3D printing technology. The other part is cost. So as we all know, cost competitive market. So how do we justify the cost? Only way to justify the cost, so we have to make some improvement on the performance, or we might be addressing the logistics related issue or any other challenges, so that it is easy for us to justify that this part can be replaced with the 3D printed component. Recently we have done one with one of the machine bracket which I have in the coming slide. So it is expensive than the conventional, but lot of logistics related can be addressed. Same with the many defense project we work with. So many of the components still we import from France or from the OEM. So all of this can be instead of waiting for a logistics time, so we can 3D print. The another one, still we are dependent on China for a casting. So where we want to get a casted component or the die. So it takes at least 3 to 9 months to get the casted component or the die or mold. So instead of that, we can 3D print that, and we can bring that 6 months to 6 weeks or 3 weeks. So that is a major advantage. For that, we should have a knowledge on identifying the part, and not only identifying and justifying from the cost and performance point of view. So then comes how do we print? So printing itself, you see a lot of paper on printing with a different direction. Each direction printing strategy will give a different properties. So selection of printing strategy is another key challenge. So in fact, what we can do is we can digitally validate that, or if I have some data, I can put it into software and understand. So once I finalize that, then I go for a DFAM. So this can be interchangeable. I'll identify the part. If there is a room for a light weighting, I will go with the DFAM first. DFAM, design for additive manufacturing. So I do the light weighting and topology optimization. Then I prepare the file for printing. So before print, whether it is in a metal or polymer, so we go for a we call it as a manufacturing feasibility study. So we can use different software or any algorithm sorry, any algorithm available. So then Then we can take this data into that and we understand whether it is printable or not. So then, no, again, so we are talking about a different set of manufacturing. So 3D printing itself has, a 6 to 7 different technology, like it can be FDM, DED or LPBF or other processes. We can check with the different set of processes. Then comes the quality inspection. So if it is a reverse engineering, I will start from here. So quality inspection either can be CMM or a regular 3D scanner. So why do we do this? To understand that as printed, it is in line with as designed. So there is no deviation or distortion. So that is the overall idea. So this is a complete 360-degree cycle of 3D printing. So as I said, you can start from here or you can start from the part identification. So most of this can be supported by the software tools, but still again it required lot of data. When I say cost estimation, we have to give what is the powder cost. So in which machine we are going to print, how many parts we are going to print. So there are a lot of manual work and understanding has to be done before we use this software tools. Yeah, so if I put a different set of process or software together, so this is how it looks. So we start with part identification, then comes the costing. So before I commit or before I start any project, so first I will identify the part, then I will get the approximate cost, so that here only I am sure that whether my work is going to be justified from technical and commercial point of view. Then we look about alternate material. Not every material can be 3D printed, and we have limitation as we discussed. Then we talk about if there is a room. So before we go into DFAM, so we should know the complete multi-body dynamics of a system. So I will give one example of race car wheel hub. So wheel hub is a very critical. It is not because all the loads coming over there, and if I replace the wheel hub with a 3D printed wheel hub, so most of the student race car, so you have a wheel hub, and every university is trying to do this. When I replace the conventional wheel hub with 3D printed wheel hub, you have to test with at least 6 different conditions. While accelerating the car, you will have a different load. While curving, you have a different load. While braking, you have a different load. Like that, there will be 6 scenarios. All has to be passed by 3D printed component. So we need a better understanding of loading condition. So once we know that, then we can talk about lightweighting and other stuff. So then we go for a performance. As I said, we have to test with different loading condition. Once I have this, then I go for a data preparation, feasibility study. Then also we can plan for post processing in the sense. So after printing, if does it require any coating. So as you know, the printing, some of the process may not give the required surface finish. Then we have to go for a machining, polishing and other things. So those things can be defined over here only. Then we manufacture and inspect. We always say that printing is a last stage. So before that we have to thoroughly calculate the fatigue life, durability, then material related property and manufacturing feasibility and the cost. So if I have all the report ready, then only we go for a printing. So this has been workflow for the OEM. So as we always look this workflow as a master chart, but if you are a service bureau, you might not be looking at all of this process. Or if I am a researcher, I am not really bothered about the design and other stuff. So my area would be more of understanding the build related and performance. So my area of understanding might be the post machining and coating. So like that we can pick. So as I said, we have in fact at Hexagon we have one we look for a OEM. So in fact I work with GE, Honeywell, Eaton in India. Then we have research and academic and the service bureau. So each one, the focus is different, but if we are a OEM or in fact we have to justify, then we have to portion of our end-to-end 3D printing technology. Yeah. So what we do, this is just to give an overview of Hexagon. So Hexagon is a Swedish company. So we are the driving. So manufacturing intelligence, this is what I represent. So when I say manufacturing intelligence, it's more of focused on industry 4.0 and how do we integrate between software and hardware. So otherwise our focus is more on geospatial and hexagon, and we control the UP dial 112. All of this project were done with us. In fact, we work very closely with ISRO for geospatial and other stuff. So this is what the portfolio, but I represent as a engineer, so our major focus is on manufacturing intelligence. So this is our presence. So you might have heard more when it comes to industry. So as I said, our presence is more in the industry and high precision manufacturing. So academic, yes. So we are pitching up now. So we have a couple of offers, e-learning and other stuff. So otherwise we are well known in the industry point of view. So this is what we do. So a lot of digital twin. If I talk about different brand, the MSC software is part of Hexagon. Then Leica camera, then Esprit. There are a lot of, at least we have 7 to 12 brands within Hexagon. So and we have our own drones and robotics, which we have integrate for the real-time application. So from the manufacturing point of view, so any questions? Okay. So from the manufacturing point of view, so what is important? The creating a digital twin. Nowadays we talk about digital twin of a any environment, or it can be digital twin in the sense replication of physical world in the digital, in the sense whatever happening on the, let's take example of a 3D printing machine. So we will be visualizing, or we will be replicating the same. The same time we can put some sensor and make it more realistic, condition monitoring. So when I get the data live, so it will become condition monitoring. First I will create a digital twin, in the sense I will create the same set of environment. Then I use couple of sensor to monitor how, let's take machining process. So what is my spindle speed? I can put one sensor and understand the rotation speed and make it visible in the software, so that it will become live monitoring, or the digital twin connected to the machine. So then we have other software where we can simulate and understand the material flow. We can understand the loading condition and other stuff. So then we can do conventional process as well, welding, joining, and effect of this process. So today we will be more focused on DFAM and additive manufacturing, and costing is another important factor. Even we say that 3D printing is pretty much adapted in healthcare and space and aerospace. So automotive, still we have a challenge because of the cost competitiveness. So R&D, yes, they do. In fact, we work with a Ford, even in Tata Motors in Pune. I was there last week to do a couple of new design 3D printing. So all of the design verification still with the machining or casting, because of the large volume and cost related aspect. But it is, presence is there, and 3D printing is a alternative solution, or it's a complementing. It's not going to replace any of the existing manufacturing processes. So why it is important? So we have been talking about the major pillar of industry revolution. So additive manufacturing is one of the pillar in the industry 4.0. We might have earned artificial intelligence, a lot of other trends, but additive manufacturing is one of the. So what we call it as cyber physics, in the sense how. So that is a major focus of industry 4.0. Yeah, sorry. So I think this you might have discussed. I was going through your course material. 3D printing. So many of student ask, sir, I'm planning to start my career in 3D printing. So how do you see from the job perspective? So we have shortage in skill, or the students are student with additive manufacturing skill. So there are many startups, they are looking for anybody passed out who is having 3D printing knowledge, at least to have a hands-on the machine and software, so that he can be directly employed. So those shortages there because the awareness of 3D printing is still not up to the level, especially for the current situation. So this is a scenario of how we started. So we started, in fact, when I was doing my engineering, it's more of a hand drawing. Then we moved to the CAD. So now we are moving to the more of a optimized or DFAM level of optimization. So we are starting with a generative design. So you may ask a question like, what is the difference between generative design and topology optimization? So topology optimization, when we use any software for a topology optimization, so it will be done with a given constraint. I have the existing part, so let's take this is my part. I have a loading condition. It will only optimize within this volume. So when I say generative design, so I can define any volume and it can come up with any shape. So there is no constraint on the volume and there is no limitation on the volume when I say generative design. That's why we call it as it can generate its own design. So it can come up with the unique shapes for 3D printing. And the advantage of 3D printing, the complexity comes for free. So if some design is not complex, better not to go for 3D printing because it can be easily manufactured by conventional way. When design complexity comes, so 3D printing can be easily justified. So this is one of the example where we have used topology optimization. So we are done with tree root structure, then lattice. So this is done with Apex generative design tool. So where we have integrated this structure together so that there is no need of support structure. So you may ask, what is AI based? So we have been climbing AI based optimization, AI based optimization. It is an algorithm written. So in this case, we have written an algorithm saying that any surface less than 45 degree need to be avoided, so that my support structure can be avoided during printing. Then anything less than 0.5 mm is difficult for aluminum material. Then I will write an algorithm saying that don't optimize any wall or any part less than 0.5 degree. So then it will use the algorithm and it will scan throughout and it will optimize in such a way that my wall thickness is always higher than 0.5. So that if you look at if I have to do it manually, how much effort I have to do, I have to manually inspect, and inspecting this kind of structure is impossible. So now we go for a AI based, or we call it as narrow AI tools, where we can give this condition so that it condition will be applied along with the regular topology optimization. So that is what we have done. What are the advantages? I think you know that freedom to design, then we get very strong and lightweighted. So we are not compromising on the strength. At the same time, it is a lightweighted structure. So customized. So when it comes to the medical, so we have done one with Manipal Hospital in Bangalore and one in Sanchiti Hospital in Pune. So when it comes to implant, so every human being is different. So we need a customized implant. For that, this is the best technology where we can print the implant. We call it as patient specific implant. So which suits for him. So not something suits for him. We try to force fit. Then patient will feel the pain. So to avoid that, we go with more customized. So now fashion industry also looking towards additive manufacturing. Speed to market. So as I said, lot of logistics related issues. So if I am importing couple of component outside India, then it can be easily replaced with 3D printing. That cost can be easily justified. So that's the advantage. So this is another example of satellite, launching pad, where we have optimized and we could able to not only reduce the weight, so we were able to, improve the stiffness, also the stress distribution. So we cannot make stress as a zero. The only things we can take care, so it is distributed, not focused at a particular location which leads to failure. Instead of that, it will be distributed throughout the component, so it is taken care by the strength. Then when we talk about the customized, so this is one of the customized bicycle, you will get it. This is a folding bicycle. If you go to their website, so you can choose the color, you can choose the different types of frame. So based on the passenger weight, they can change the frame. So all of this, because this is a folding bicycle, they will carry. So it has to be as light as it possible. So these are the things which we are doing with 3D printing. And as I said, if it is not complex, then it's not suitable for 3D printing, because it cannot justify that technology and the cost we spent. So pain point, so it is always hard to justify from the cost point of view. As I said, when it comes to the performance improvement, so it is easily justified the cost. So otherwise, we are always questioned, why do you want to go with expensive processor? A lot of questions will be raised on the performance point of view. So we have to spend a lot of time on proving that yes, it can perform better, and we don't have any standard as of now. So that is another things. So we always, what we do is we test the quality and we will put it into the system. So in fact, what we always say that we do the CT to understand the material strength and the internal dimension. So once we have the CT, so that is a qualification method we follow. So then, as I said, the whatever points we have discussed, so this is already available. So I was mentioning missing expertise. So that has been still, the concern for us. So we have a lot of resource gap between what industry is looking and the people trained on the field of additive manufacturing. So this is one example, so which we have recently done for one customer, and this is just to say that maybe I'll ask you. So how many of you think that yes, this is a good optimized design? So don't raise your hand. So that's also fine. So what we are trying to say here, see, as I said, when the design is very simple, when it can be conventionally manufactured, so it makes no sense to put all our effort and come up with a topology optimized design. So this is not the right design, because the printing time and the complexity is higher than what it can be done conventionally. So this is just to show that when we cannot justify from the design point of view, so it is not recommended to use the 3D printing technique. So also we have to do the part integration. So instead of having single part, we can integrate 3-4 part and get it printed. So that is another advantage which we can get from the 3D printing. So now let's, any questions so far? No? Okay. Yeah. So cost is dependent on 3 factors. One is volume, as you said, then the material we use, and MHR, in the sense machine hourly running rate. So these are the 3 factors. So and it changes from machine to machine, regional wise. So if I get material from the local supplier or the OEM, the cost will be different.
Like if a client comes with you a 2D design or a sketchy done, you will convert it into 3D first, then you will take cost, and then you will do printing.
Yes. So first we have to get a 3D model, because we need a volume. So then we take that into the software, or even we can calculate the volume. Then what is the material required to print that component? Then what will be the material cost and machine cost? So machine cost includes the energy consumption and labor cost and other things. So that is how it is calculated. You can do it in Simufact as well. It has one module called cost estimation. So it can do that also. You can have a local cost also. So top of it, if you have post-processing and material loss, you can give that percentage as well. It will predict very accurately. So that we can do. Yes. Any other question?
This STL file is there, sir?
Any native file format. You are asking.
STL file is there?
STL. So you can use STL, step, parasolid, anything will be supported. So there is no constraint on the file format.
Not mandate.
Any file. It's an open tool kind of thing. So any native CAD file can be imported. I may have one slide. I'll see if I have that slide. Okay. So this is, we call it as the generative design cycle. So when I say topology optimization or DFAM, so before that we start with the initial understanding of the design and non-design space, in the sense where are the area where I am not allowed to remove any material, because it might be fitting into the another body, or we may have to integrate with the main system, or this might be the load bearing areas where we are not allowed to remove the material. Also, not only that surface, the surface surrounding 5 mm, 10 mm, we should not do any optimization. So that is my the first, before we import any geometry. And then intelligent smoothing. So all of this is done with a narrow AI tool. Intelligent smoothing in the sense, now let's say we have given the problem statement to 5 students. So each student will have a different meshing condition, and he will put the same load, but result will be different. So instead of that, the software will come up with its own meshing and geometry cleaning, so that whenever you apply the same load, so 5 out of 5 students should get the same fatigue life. It should not vary, because I am not varying the loading condition, I am not varying the geometry, but still my result will vary because of the mesh. To avoid that, we have introduced this intelligent smoothing. So what it will do, there will be predefined algorithm. So the sharp corner has to be, it's more like a thumb rule. Wherever I have a sharp corner, it should have at least 3 mesh element, if it is a TET element. So in the flat surface, it can go till the ratio of 1:3. So that my meshing in line with the basic principle of how much element has to be there in the sharp corner, what should be the element size in the middle of the component. So all of this will be taken care. Now if you go for a the design candidate, and you want to export and see the manufacturing feasibility or the durability, you will have the unique results. So you will have the unique result if you include manufacturing feasibility, otherwise it will be the same. So it is not different for each one. So now we talk about how do we print. So now we understand the loading, meshing and geometry cleaning, then the topology optimization, then this talks about durability and the printability. It is not always true that any design can be easily 3D printable. So it will have its own challenges when we have a internal cooling channel, the wall thickness which is less than particular dimension with respect to the material. There might be buckling related challenges. So I may provide, if you look at closely, this is a support structure. If there is an internal cooling channel, if I generate a support, how do we remove it after printing? So there will be challenges from the manufacturing point of view as well. So that can be taken care by understanding, or just we always say that first run a thermomechanical simulation to understand the manufacturing feasibility, then we can go for a final design validation. Manufacturing feasibility itself, we have a lot of parameters to consider. What is your printing strategy, what is the material, and what kind of support structure you use, whether it is a solid or cone type. So there are a lot of other parameters which can influence the part distortion and residual stresses. So this performance of the part. So this is what we have to do when it comes to the optimization. Example of as I was in the previous discussion. So this one of the wheel hub which we have printed locally. At least I have 6 to 7. So this could be one of the interesting component. If you have a, I'm sure every university has one the student formula car. So now it's a challenge that the lighter the wheel, you will have better cornering efficiency. And the mileage, but mileage we are not focusing. So now we have better handling and cornering efficiency. So we are trying to optimize that wheel hub, and we are trying to replace with a 3D printed one, so that we will have a better performance of our race car. So this is one. So student can take up and optimization challenge. So we can work on that. So as I said, when we jump into it, so we have to start with multi-body dynamics to understand what is the vehicle is designed for, what is the weight coming to the each, the wheel joints, and this wheel hub same time it is critical. It is connected to the suspension, it is connected to the brake pad, and it is connected to the wheel, and a whole vehicle load is coming to this component. If it fails, the vehicle will stop. So we have to take both the loading condition and DFAM into the account, and we can do further optimization. So this just to show that when we use tool or when we don't use AI based tool, so how much effort I am putting manually. So if you look at one on the existing software, so now you have to run with 3 to 4 different software, one for topology optimization, one for meshing, then one for design optimization, manufacturing feasibility, all of this. So by the time you run through the different software, each time you have to save the result, export and import. Sometimes it will not be compatible, file format will not be compatible, then you will have a lot of data loss. But all of this can be eliminated using the AI based tool. It's a open AI in the sense, when I say Apex, limited to the only lattice, or any honeycomb structure. You can come up with your own structure, or you can come up with any unit cell. We call it as a unit cell. I have one unit cell per volume, then it will be replicated throughout the body. So you can come up with any unit cell. So that the manual effort we put on the meshing, geometry cleaning can be eliminated, so that I save at least 80% of activities, which is of geometry cleaning and other stuff. So that's what it says. So 6 days. So that we should focus more on the engineering stuff than non-engineering stuff. So this is how it works. So mesh generation is automatic, and then we have to only define the constraint and optimization. So what is my optimization goal? So whether I am doing it for a metal, polymer, or what kind of result I am expecting from this, then it will do the smoothing and the repair automatically. Then with one click, export the STL file. Not only that, somebody can ask me a question, STL is a non-editable file format. Editable file format. Then you can generate a NURBS, in the sense you can mesh it and make it as editable. So that is another advantage. So any editable, you can convert it into editable file format. So this is a automation or narrow algorithm written. So why we use or not of non-engineering stuff, we will give it a job. So this is what we have a lot of automation in the topology optimization. Trying to understand what do you mean by optimization. So what it does, how does any optimization tool, it is not specific to one tool. So it's about technology. So what it will do is, currently I have a component. Can you see here? I have a component. For any optimization, I need one component, one force acting direction, or one loading condition. and one fixed point, or you can give fixation as another geometry, or you can fix a body. So it will apply the load on the given component, then it will understand how the stress distributed within the volume. So every material has its own UTS. So it will compare the stress with UTS in each element. So wherever it is less than UTS, it will remove or delete that element. So that what it will become? It will become lighter. Can you see? So these are the area where the stress is less than the UTS. So it removed. So again the same set of load will be applied. Then further iteration it will remove further material. This is clear? Any doubts? So this is how any stress based optimization tool works. So in optimization there are many. So what we have been discussing is only about structural and stress. There is a thermal optimization, there is a frequency optimization, then optimization can be co-simulation using multiple optimization in a single body. So all of this were feasible, but we start with a stress based optimization because this is critical from the load carrying and fatigue point of view. So thermal and other things can be optimized later. So now the same type of loading condition will be applied to the larger component. So this is I chosen just to explain that how this optimization works. So and I can pick internal iterations as well. And if you compare this with the original, you will have a lot of weight savings in it. So it means to say that this material is enough to handle this much force. So that is what it is justifying. So how does this complete optimization or DFAM funnel works? So we have seen stress based optimization. First it will check the stress throughout the component and it will add, subtract or add the material. Then it calculates the weight, how much weight has been optimized from my original design to the final design. Then design complexity, because we have, as I said, we have written lot of algorithms saying that you don't optimize less than 45 degree, reduce the wall thickness, all of this will be checked. Then the manufacturability. So when it comes to the fashion industry, they are not much worried about fatigue, but they are more interested in the unique design they want to get out of 3D printing. So they want to have a unique design or unique looking design. That can be also one of the condition. So these are the condition during manufacturing process. So that any design I have, so it will satisfy all of this condition and it will come up as a final component. So top of it, if you want to add your other aspects also, you can add it. So you may say that you want to optimize for only one material. You may optimize for cost also, you can add it here. So this is a complete DFAM workflow. Start with the stress to the manufacturability. So these are the different design. So you might have already seen how do we use the lattice, tree root structure, honeycomb, and the whatever you see on the right, all of this will be done automatically using the algorithm. The smoothing, the geometry cleaning, then converting STL to the step file. So all of this will be done by the software. So you have to only spend time over here. So rest of the things will be taken care by the software. So this is a kind of advancement we are seeing now. We talk about meshless optimization. So in fact here we know there is no manual meshing, but there is a meshing in the background which is done by the software. So then the automatic cleaning of the geometry. So now we spend only on the few clicks and we will be more interested in understanding the part performance than the geometry and other stuff.
But what about the dynamic loading? The optimization is done majorly on
Static, yes. So now what we do is, so once this is done, generally what we do is we start with the multi-body dynamics. We choose the maximum load in the each direction, so that we take it for optimization. So once we have this, the final shape, then we put it back into the multi-body dynamics. Yeah, it is a part. Yes. So as I said, MBD, frequency and thermal can be added. The first point, so what we try to make is we simplify the loadings, we take maximum in each direction, then we optimize it. Yeah. So this is another example of the same loading condition and I want to optimize for a minimum support structure. Let's say I know that I will print this part using 3D technology and I want to optimize, I want to print with no support. There are a lot of algorithms. So now you can see that you can make it as a no support algorithm active so that it will optimize in such a way that when you print it, you require very minimum support. So that your material wastage will come down, the powder cost will come down, other stuff will be done. So this can be done during design stage itself. See, during design stage itself, it is good to have the manufacturing principle during design stage. Otherwise, I go to manufacturing, fail and come back. So that approach will take very long time. So that manufacturing constraint is considered during design stage. So let's look at couple of case study. So this is just a comparative case study in the sense when we focus only on the topology optimization, we are limiting ourselves. When we are open for a generative design, when I say software that this is a loading condition and this is a material you come up with any design, then there is a more room for getting the very lightweighted design. So we always say that go with generative design, not with topology optimization. So this is one of the GE bracket challenge. So every student can take that component and try it. So these are the most of the example I show, it is implemented cases. None of this only the software cases. So we have optimized, printed and validated because we have that machine and the measurement equipment. So this is one of the TSAT satellite bracket where we had a major failure during the launching. There was a crack here. So what we have done is we understand the initial design, then what is the design and non-design space, load comings over there, so what are the different kind of loads, then we optimized and we could able to print. So during this we were able to save the weight by 50%. The same time we are not compromising on the strength. So in fact we made it more stiffer and at the same time we focused on how the stress is getting distributed. So that is something we have to take care. So if that can be done, then the lot of failure related during the application can be avoided.
What does your validation involve?
It's a fatigue or life validation. In the sense, after how many cycle. The advantage of space and aerospace, there is not much fatigue. It's a one-time application. So we will just look for. But another limitation, they say that instead of UTS, you use the yield. We should not even go to the yield point, even though it is one-time application. So we limit to the yield and we put safety factor of 0.2 or 2.5 so that it is easy. So that's why I said AM is very much adopted in space, aerospace and medical. So this is another example I think now after post processing. So this is how the optimization runs. So automatic smoothing, understanding of stress, multi-body dynamics. So all of this will be done in the single platform. And it can be integrated with other tools as well. We always say that we won't compete with any of the software tool. So this result can be directly interpolated with LS Dyna, even though they are competitor. It can be interpreted with Nastron Solo 400, which is well known for a space application. So we have that integrations. Yes. So when it comes to the validation, that is a major input. It has to be taken care. Because first, so the optimization runs on the material characterization only. So when I start the optimization, I will give the CAD file, then I will define the material property, what is the yield strength, what is the Young's modulus and other stuff. So based on that only it does the optimization. So what we are missing here is manufacturing effect. So when I do the heat treatment, again property changes. That is the part identification software does. That will suggest alternate material. What it will do, when we select the part, no, it will compare the 10 different material which is equal, having equivalent properties.
But functional requirement, you define it, you define the design as well as material.
Now, as you rightly mentioned, sir, what I am doing is, this is my initial condition is application requirement. Now it will screen select the material. That's what it does. But when I further optimize,
You don't select the material.
okay,
This is your functionality only. At the end you tell that this is the material requirement is required for me.
okay,
Can I give the material or not is my problem.
okay. For that we have something is very much valid for a carbon fiber composite. Now I know the strength required. Now I can develop my own material with a different orientation. So that is more useful for a composite, as you rightly mentioned. So now I know the optimized geometry. So now I know what should be the material strength. Now I go back and develop my own material. That can be done. But it is easy for a composite and other things. But in metal, it is very hard to come up with my own material grade. Because recently we have done one with ISRO, printing aluminum alloy with ceramic. We were not able to even print 10 into 10 coupon. So we have tried all of this. The material requirement is it should have some thermal conductivity plus the aluminum property. Now when I try to develop a material development is a big, when it comes to metal, it is not that easy. No, we have done. For a composite, as you rightly mentioned, we have a tool. It will say that this is a required property. You choose any material or you develop your own material.
But in manufacturing you are able to precisely, you are able to localizely, you are able to control the structure and graded properties you are able to develop it. That is possible, okay?
So
You can design
for a 5 to 10%, by varying the printing strategy, we can vary. But that alloy will have its own properties. That is very difficult to.
In case you look at disk, okay, disk is you want equiax structure, blade you want syndication. Is this possible? Okay?
Yeah,
That means okay, you are changing the entire range of properties and a given material.
so
By changing the structure, you are able to get that.
that comes in the post processing, as you mentioned.
Processing, you cannot do anything at all.
So we have done.
Only you are doing.
Okay. But the base structure is very hard. That's what I also felt, because we have tried and failed many times. So that is easy. Software can throw anything. That is easy. It will tell that this is optimized structure. You come up with any material which will suit this requirement. But as I said,
For a given material, you are trying to optimize it.
no, even without material we can optimize, as you mentioned. So for this one, let's say I will not use any material. For this structure, for a 10 kg load is coming over here, you come up with any material which is having 320 MPa strength or yield. So now it is your choice to choose. So that is possible. We call it as, there is a good name like grade down, material grading kind of things. They do this kind of project. The advantage is, so instead of going for a higher grade material, I will go for a lower grade material which will satisfy this condition. So that is the grade change project. This is called grade change project. So it will only tell the properties. I will choose the grade. So that can be done. So this is whatever we have discussed, lattice, all of this are predefined. So now I will inspired by nature, and this one of our customer who said, I don't want to use any existing optimization algorithm. I am inspired by this tree and I want to use this tree root structure for my design. So that is what we have done, and you know that there are many naturally inspired, honeycomb is one of the example of how we inspired by nature. Then we use that tree root structure. When we reverse it, so you don't require any support structure. You use this tree root structure so that part can be printed without any support. So there is an inspiration from nature, so then we have to use the same. So this is a conventional design. So now he said that no, I want to use, let's replace with this tree root structure so that I don't require any additional material, there is no printing related challenges. So it can be printed easily. So we have done all of this. So this can be done in Apex generative design. So this is a tree root which we used for 3D printing. So this design doesn't require any support because this itself acts like a support. So then lattice, not only lattice, varying lattice with solid plus lattice, tree root structure. So this is almost saved 60 to 80% of the weight, and we have printed with aluminum material. So this is how we printed it. We printed and we give this to, we run one of the program called, our student will come and present in our user conference. We give this trophy to the best paper presented by the students. So this is how. So what we are trying to explain is, you need not to restrict yourself for only lattice or honeycomb or any other structure. So you can build your own unit cell and come up with the design. So this is the advantage of the software tools. We have seen this. So this is the one which we are discussing, sir. Now I scan the material, I know the loading condition. So it will tell what is the required property. Now you can develop your own material. Use a print a coupon. So this is pretty much possible in composite, because when you have a different carbon fiber orientation, you will have a different strength on that particular direction. So this can be done when we do. But for metal still, there are a lot of justification has to be provided. For composite, it's very easy. You know the unidirectional and bidirectional strength, you can develop your own composite material based on the application requirement. You know the passenger weight, you know the dimension, now you develop your own composite material and give it to them. So that can be done easily. So this is how it was done. So material selection based on the application requirement. So this is pretty much can be possible. So this is what we are saying. When we are choosing, it is not only strength, the manufacturing process will come into picture, the part performance and the behavior. So all of this has to be taken into consideration. So then only we will be able to succeed. Otherwise, I can choose a material, but it is not, let's say copper, but not printable. So what do? Ceramic plus aluminum, not printable. I can address the application requirement, but printing or manufacturing is a challenge. In sometimes cost is a challenge. Like that, if you can integrate all of these three, we can come up with our own material grade. So this one you have seen, you will see in any of the high-end car. It might be Japanese or German. So this is called a light hinge project, which we have done for automotive automakers. So this is almost pretty much 70% 70% weight reduction. This is done with 316L material. So which was successfully done. You will see it in Japan and German cars. So this is wheel hub. So I have put this. So it start with topology optimization, manufacturability, and the multi-body dynamics. Otherwise, with topology optimization alone, I cannot say that yes, it will give the better fatigue or durability. I have to put under multi-body dynamics under different loading conditions. So we have used Adams, which is well known for multi-body dynamics, and we validated that. So this is a complete cycle So start with the initial design, find out which are the design and non-design space. That is critical. Where are the area where I can remove the material, where are the area I am not allowed to remove the material. So then we have to run through all of this process. Then we will be able to successfully replace conventional part with the 3D printed. So this has been done, I think, 5 years ago. Now, as I said, you will see every university is trying to do this. This is a workflow. It is not just one step. So we have to run with multiple DOE, in the sense selection of different orientation, printing strategy, different material. Then we have to compare all of this together, and we have to pick one of the best design out of it. So this is how it was optimized, and this part is already running from last 4 years. In fact, even in India we have done multiple wheel hub optimization. Yeah. So if you want to really look at end-to-end process, so this is how it runs. So this is a complete workflow of DFAM, material selection, and 3D printing. So start with your initial drawing, convert it into 3D, do the optimization, check the performance, then manufacturing feasibility, prepare for a printing, print, measure, then quality inspection. If you require further correction, you can do it, then post-processing. So this is a complete cycle of implementing any 3D printing into the application.
Real quick, in this cycle, because I'm kind of having the same kind of question that at what point does material selection come in this flow?
Here, performance and the generative design. So now, sir mentioned, if I have just a property, I can choose 10 different material and see the performance. Geometry is fixed, but my material is not selected. So now the same geometry I will put aluminum and 316 and I will see the performance. So aluminum may run for a 10,000 cycle, steel may run for a 12,000 cycle. It is my call to say that what material to be used.
But isn't it also true that when you are optimizing the design, you cannot be agnostic to the material? Because some elements can be thicker or thinner depending on what material.
So initial material property we provide. So that is a base. So when it optimizes,
Which means you have already chosen the material.
we have to choose some default value to start with.
But that is where my confusion lies. Now, I mean, if you are picking a default value, it means you have picked the material in some way.
So if you don't want, you can run only one step. See, these questions we have been working with industry.
Right.
This has already arrived. It's not something new for us.
Yeah.
Let's say you want to eliminate the material selection and you might be interested in new material development. I know the application condition. I will come up with my own material which is better than any material available in the market. That's what we did with the ISRO.
So no need to, we are not going to change the material, for example, okay? But we can location specific manufacturer can change it. So by modifying the things and optimize it, that is another advantage of everything.
Then we have to split the part, then give a different property to the different area. That can be done. You have to split the part and give a different property. That is the best way to do it. So that is feasible. Now, you want to be material agnostic or you want to run your design is finalized.
That means material is not design variable in this case. So it is a standard.
It is variable. It is not a standard. You can define anything. Let's say, there are two ways of looking at it. One, you define the material and run it. Other way, you understand the stress generated and develop the material to that level. Now, I don't know, maybe if I have a marker I can write and...
I think it is there, sir.
Okay.
The body.
Can I get a marker?
Given material
there are two approach. As I said, I'll explain. This is okay. Here I have a cantilever beam. I'll so this is 10 kilonewton. So now what I will do is I will not define the material. What I am interested is when I apply 10 kilonewton, what is the stress generated over here? So let's say it will bend like this, and there might be more stress generated over here, which is of 320 MPa. So my target is I have to find out a material which is having yield strength of 320 MPa. So now we are choose. So now material is not selected. So I am coming up with a material requirement for a given application. My application is I have to design a structure which will stand for a 10 kilonewton. To stand 10 kilonewton, I need a property which is having 320 MPa of yield. So now my material requirement, I am deriving material requirement. So I will derive yield. So this is 320 MPa. Now the next, so I can do the further optimization, or I can consider the elongation limit. So that could be 20%. So I will consider the elongation limit, or I will call it as E or some factor. Then I will talk about so what will be the Young's modulus and Poisson's ratio, or I can just call it as epsilon. So now I have to choose for this condition. So let's say 0.3. So you can develop your own material which satisfies this condition. So any material I develop, it has to be 320 and above. If it is less than 320 MPa of yield, it will fail. It is not suitable for this application. So for this, what we do is,
But if you can change the stiffness in between the way you design it, even the lowest limit also can be fine.
yes, we have to give that as a variable.
Structure, like the way you design the lattice structure, lowest limit also can able to meet the 320.
You can rerun the one more optimization cycle. It's an iterative method because we have to fix at least one variable and do the analysis. So with this, as I said, we included electric conductivity, other stuff. So that is what, as I said, one aluminum versus ceramic. So again, your variable can be thermal also. Now you say that I want to include frequency response also. Why only stress? So those things is iterative. We can do that iterative, and as I said, it's easy if it is a composite. It's a straightforward. Yeah.
Sir, you have quoted one example that Tata has used the optimization component.
Mhm.
May I know, can I get to know how many years they took to finalize the design, like start from the design to testing and application, real-time application they use the automotive component?
So as I said, it was used for prototyping. Not only that, even tire industry, the tire mold will be 3D printed, but actual production will be done with machined or casted component. I think the project duration was 4 months or something like that. So prototyping, you just want to prove the concept, or you may want to see the functionality and integration of the component. The same project. Okay.
He told that from real-time to design to testing component, it may take some 5 years or something to use it in real-time conditions.
Real time, they are not at even now they are not using any 3D printed. So
They are not ready to do. He told that there is some SLA something.
Yes,
like-
yes.
So they can get, so they can use it for the mass production component like that.
yes. So nowadays they need a new model in 2 years kind of things. They cannot spend much on R&D. So speed up all of this only they are going with prototyping with 3D printing technology. So actual production will have its own pro and cons. Yeah, so this is the overall cycle. So as I said, you can either start with reverse engineering and re-engineering, and it is not straightforward as you look in the screen. So you have n number of variables in each stage. Now we are talking about only material change. You can ask me, I will change my printing direction and the support structure. So it can also affect on our final part. So like that, we have a lot of variables throughout the cycle, which need to be taken care. The best way to, you have to digitally validate with all this variable and you print right at first time. So that's the overall idea here. And you have to use at least 5 to 6 different tools during this. So this is one of the example which is already done. One was designed for plastic, one is designed for aluminum. Yeah. So and this is a recent one of the cold plate used for electronics, which we have optimized with N topology, and we have understand the heat flow and other stuff. So far we have seen is more of stress-based optimization. This is thermal optimization, where we take the thermal and not only thermal, we can integrate the co-simulation. It is called a co-simulation. Structure, thermal, then fatigue. So all of this can be done on the single component. These are the other example of how we can optimize and further validate. So we always say that lattice looks good, the any unit cell looks good, but when it comes to the fatigue, those are the weak points. So we have to be always careful. It looks fancy, but the more the connecting points, it's a weak point. So calculation of fatigue for a lattice is a very impossible task, we can say that, because each lattice is a one connection and is a weak point. At every corner I have a weak point. It's very critical for a vibration. If I put a lattice into vibration, it will fail like anything. So these are the points we have to take into consideration. Where there is no rotating or load bearing, lattice is very good. But when it comes to load bearing point, we never say that use the lattice, because we have seen failure, and vibration is another challenge for any of this lattice or any unit cell. Vibration is a challenge. So we have to be careful, and this comes when we try with experience, it will come. This is another manifold which is already in space. We are allowed to show, but not the dimensions. So this is another example which we have done with Space Agency. So now this is again coming to the DOE analysis. Now we have too many variables. So my variables can be geometry, my variables can be support structure, my variable can be material. So how do we come up with the optimum process or material? So what we can do is we can run a AML algorithm, so our sensitivity analysis. So understanding that what is my each parameter affecting on the final part performance. So it can be residual stress, it can be microstructure. I think whatever we are discussing, it's already done. So what is the influence of each one on the final material property? So this one of the paper published by RMIT. So they have used our software and they have done all the microstructure validation. Yeah. So before that, we have to run through the conventional way of reducing the run order sensitivity analysis. So it is more of a next version of statistical tool than sensitivity. So it is a new word given, but the base is same. It is a statistical tool where we use this optimization. And this paper is available in elsewhere as well. Yeah, this is a paper. The printing strategy, then reheating, and the microstructure. So all the correlation is already done with using the software as well as physical validation. So it is done at RMIT and available. So what they have done, so in fact a couple of team members were part of it. While printing, So how the subsequent layers are going for a heat treatment. So because of that, what is a grain change? So then grain, they are correlating into fatigue and creep. So if I have a finer grain and coarse grain, how my fatigue and creep life is varying. So for this kind of study, AAML is essential. Otherwise, you will have 200 and plus variables. How we cannot conduct, yeah.
You may get a tensile strength, but you may not get the required stability. There is an issue in this.
Okay, okay.
Because you are getting big grain, okay?
Mm.
If the grain is so high, you may not get stability.
Yeah.
Strength is possible.
Again, they have to change the grain size, vice versa. Yeah, that is, as I said, it's a DOE. There is no straightforward. So they have to run a DOE analysis and they will be able to do it. So this is one of the example which is already done. And now, we talk about only structural. What we missed is the manufacturing point of view. When we have a different printing strategy, how do we correlate that and other stuff? So how much time I have? Another 10? Another 5-10 minutes? Okay, okay. So how do we take that into consideration, like lack of fusion? See, my design is perfect, material is perfect, but I have a defect during process. So those things can be analyzed. See, all of this can be done physically, but if I say I have 200 variables, I cannot print 200 coupons or part. So that we used AAML to come up with a reduced run order. Then we print only that, rest will be done by the software. So that it will be, combination of software plus the physical printing, so that our prediction will be very accurate. So that is the overall idea. And we have a mesoscale simulation which can predict the lack of fusion defect. Also it can say whether the chosen parameters are correct for a given material and whether it will fall under a stable zone or defect free zone, balling effect. So if I am doing more of a material related optimization, so that can be done over here. And lot of development has been done on the aerospace and space point of view. So we closely, you name any global OEM, so we are closely working with them. Most of the modules were generated for a commercial, later it is given to the public. So as I said, Nastron is a NASA structural code for a space application. It developed by NASA, then Hexagon purchased, made it commercialized. So like that, there are a lot of advancement happening where how we can use AAML for manufacturing. Once it is proven and once it has become patent free, then we will give it to the public. In the sense, all our customer can use that. So, and as I said, we are not only supporting from software point of view, we have something called Material Center, which is used by US Army for a testing, and all their data will be managed by us. If I have a 4 research business unit in the same organization, let's check Safran or GE, they have technical center in India, US and let's say in Europe. So there will not be any repetition of the test done. So all of this will be uploaded over here so that the colleagues can access any of the relevant test. It is done by within the organization. So those facilities also there. And what does it include? It includes machine information, any new material development, property related if I am working on a new material development, then the manufacturing related part detail and what kind of process we followed. All of this will be available in the cloud-based platform within the organization. So yeah, so this is what we learned today. So I'm almost end of my presentation. So this is one of the drone startup in Bangalore. We have optimized for a drone. So this is a place for a battery and camera hold, and we have printed with SLA material as well as with FDM for a proof. And this is a bionic design for a medical implant and other stuff. This is a industrial application using DFAM. So all of this were DFAM examples. Couple of other design which we have used. This is a wheel up which we are talking about. Other things Again, this 2 hour wheel up, this is for a aerospace application, then application of tree root structure, satellite and other application. So you can come up with any of this design, not only lattice, varying lattice plus solid and other stuff. One is applying lattice, but after applying we have to ensure the durability and stress. In fact, we can do that. So if you have any further doubts, you can just write to me. So you can write to me or our global expert. So whatever we have seen is more of a industrial. So what we do for academic, I have a couple of slides for academic as well. So now we have come up with SIM Academy under Hexagon, where we do the certification, collaboration and connect. The program is called. So this is already implemented in RMIT and many of A-Star University and other colleges. So where we run the program, so this structure is already available with us, or you can replicate the same what it is already done in RMIT and other stuff. So if you are interested, I will connect to the respective team, so who will be looking after this curriculum development and the software. So this is our development in industry, so which is already done at CMT digital twin. The same part designed for a casting, machining and 3D printing. So all of this, the same set of loading condition, but a different part which will be done with a different manufacturing process. And the inspection using robotics. So this is more of industrial application where we create a digital twin reverse engineering for additive manufacturing process. So going forward, so you need not to use or install any of the software. So all of this will be available on the cloud, which is called Nexus. So all the tools and the data preparation software, everything will be on the cloud. Each students or faculty will be given with the login. You just have to log in and you open that software. No need to install, no compatibility issue, nothing. So everything will be on the cloud. So only challenges with the defense and government, they don't want to go for a cloud as of now because of the security purpose. But this is already available and many are moving more of a subscription and cloud. Cloud credit will be there. So it will be some free credit. So after that it has to be pay for usage. But for them to experience, it is easy to log in. They can log in as a Nexus, hexagon.nexus.com. If they can go, they can log in just to understand the workflow and what are the tools available. And third-party tools also now integrated with this platform. Yeah. So, and more importantly, so for our existing customer, we run something called a 6th sense. So where our existing customer need not to be the customer in the sense any user can come and present their idea. So let's say you have come up with your own unit cell design and you want to make it commercialize. So we have chosen one from IISc. So there is one professor has come up with one of the concept of, it's called EMI, the emission measurement index. When I have an electric component in the system, how much it is emitting for a surrounding component. So now we will be, Hexagon will be acquiring that concept and we will fund to develop that concept. So patent discussion, other things will be discussed later based on the funding. So if you become customer, you have chance to participate in 6th sense. So whatever idea you have or any unique concept you have, so you can come and present, the rest will be funded, will be done by the Hexagon. So one we selected from battery range calculation, another which is, this year there are 2 ideas selected from India, one from IISc, one from another professor, I don't remember, but the concept is on calculating the vehicle range. If I have a vehicle which is of let's say 600 kg and if I have a 66 kilowatt battery, so what will be the range? He has come up with some equation and basic algorithm. So that will be funded by Hexagon to develop as a commercial tool. So like that we run this every year. So if you have any idea, just come register to 6th sense and you will be get a chance to present and it will be funded by us. And you have a lot of white paper case studies available in your website. If you are interested, just go through that. Yeah, so with this I will end my presentation and I Thank you for your time. So if you have any questions, I am open. Or you can write to me as well. I will just. Okay. It is there in the first slide, so you can write me. And it's already printed in the handbook. Yeah. Any questions?
So the software can be used as the artificial intelligence, right?
Yes.
Suppose if I am sending my original design to optimize, will the software able to identify whether the design has a scope to optimize or not optimization?
Yes.
Without the simulation, before that only it will identify.
So it will stop at one point saying that, so it's a iterative way. It will keep on running. So when the last iteration and next few iteration has seen no material reduction, it will stop saying that there is no scope for a further optimization. Now you can come back and do any modification. For example, you have not chosen the material. Now you choose the material. So then it will rerun. So like that. That is open.
One more is that apart from this generative design and topology optimization, this software can be able to identify like conformal cooling channel, part consolidation.
That is thermal management. That can be done. So it can be done because many heat exchanger were 3D printed. We have done. I have a live example with Bharat Forge. We have done that conformal cooling. So not only optimization, after printing, how do you ensure no powder is struck, no material struck inside a conformal cooling channel? That we have done it. I have case study. If you can, I can share that.
Sir, finally, which one is better compared to subtractive and additive?
When the complexity is high, additive manufacturing. In complexity is simple, subtractive. So additive manufacturing, we say that it is not going to replace anything. It will be complementing, because complex design with conventional is difficult. So there additive plays major role. So it will be one of the substitute. It will not going to replace casting, machining, no. Because many 3D printed were machined for a better surface finish. Yes.
How an educational institution can associate with the SIM Academy?
SIM Academy, I will forward those details. It is more like if you have any, you might be using any of our tool. You might be using Adams or Nastron. So if you have any idea respect to that, you can go and register. So that it will be screened. So first India level they will screen, then they will take it into the global and they will fund it. So that is open. We have live example of emission calculation and the range calculation. There are two projects which is already funded for India. So that is going good. Yes.
Sir, you talked about rain process simulation.
Hmm.
So which type of process? I mean, basically is it LPBF or are you simulating other anti-manifold?
Other also. There are 6 to 7. I can simulate FTM, SLA, TED, LPBF, then binder jetting. So these are the different module, because in the background science is different. The material we use, in DED we use wire or powder, in LPBF we use wire, then SLA and FTM we use plastic. So these are the different module we have to choose based on the application. The same design, what you can do is you can put into all of this and understand which is better. That also you can do.
Also, which type of support structures are, I mean, basically LPBF as well as FDM. Which type of support structure is being used for simulation?
Yeah, support structure, that itself we have, if you look at, we have solid cone, then,
This is there, tree is there.
So what we always say that where there is a more load coming towards the base plate, we need solid. Where there is only overhang, there we use this cone. So further you can optimize using local support. Instead of giving support from the base plate, you can give local support as well. For that you have a lot of software like AM Studio, Magix, even SimuFact. So those software need to be used for a support optimization. Yes, you're asking.
Can we get this software for research purpose? Because we have a machine and we are facing difficulties in simulation and all those things.
Yes,
Can we
that is SimuFact is a right one for a machine.
Is there any trial version for students?
Might be available. So trial version, what happens? You will not get the third-party tools integrated in the software.
Yeah, whatever
But you can try.
that we can.
Otherwise, you can write to, you know, who is the contact, or you can write to Samir and get the research license only. That is
We
possible.
have a machine is there, but we are somehow we are failed in the analysis and all this.
You can do.
We want to explore it.
That is a major application. It can be done. You name any service bureau in India, intake, everybody asks this tool.
That's why.
Yeah, you can do that. Yes. And it's an outcome of, it's a spin-off of SLM researcher from Fraunhofer University. So they developed, I think, 12 years back. Now we are commercializing it.
Is India, Hexagon India recruiting any students having AM skills?
We have our own recruitment. Also, there are many of our customers who is looking for it. So, if you have anybody, we are happy to.
Share the CV.
Yes, yes.
Please help us know some of our students are working in that area nowadays.
Recently, I have put WhatsApp status. Anybody with 1 year experience, please reach me. There is a requirement, as I said, even for a startup. So they might be having good experience in design. AM is something we have a shortage of skill candidate. That is there.
Yeah, but unless they work in any industry, they don't get experience, right?
Yeah, that it.
But their PhD, that's
Yes.
research aspect.
But nowadays, if you see, most of the colleges, they are also investing on this. So AM lab setup. So good to see. Many engineering colleges have a metal machine, which is expensive. So one. So like that. So previously it was only FDM. Somebody used to buy desktop. Now metal machine also investing and lot of research. So going good. Any other questions?
Sir, is it possible to optimize the medical implants like a TKR and
For that we need a CT scan data. It can be optimized, but we need CT scan data. If we have CT, it can be done. So there is one YouTube video you can go and watch.
Sir, I saw that most of the doctors they will not show the patient this is implant nothing but titanium, aluminum, nothing but tungsten. They only give the treatment and how the implants are sustained in our body.
That they have tested already. They have taken a safety factor, all these things. I think they have.
Before implanting, they're asking sir, which material you want.
Whether you want titanium, gold.
Most of the hospitals they're asking.
Yeah, that is true.
Which material you want. Based on
So,
the cost you
that is designed actually based on the even I was there in one of the hip replacement. So they will consider the weight and other stuff. They know whether it will withstand. Most of the time it will withstand because that is designed for that.
Yeah, if there are no queries, we thank from all the department as well as from the organizing team and the participants. Like Santosh has came without hesitating. With one word, he has accepted our invitation, and from Bangalore he came here to deliver. It's very thankful on behalf of our organization. Thank you, sir. And regarding, also we have Professor Madhusudan Reddy sir. He is DMRL director earlier. Now he is adjunct professor. You can interact with sir also if you have any doubts regarding this IT manufacturing, welding as well as. Thank you and all. Okay. And regarding the afternoon lab sessions, our lab one is wire architecture manufacturing lab, another one is powder bed fusion lab. Okay, we'll be at 2:30. We'll go to WAM lab first, wire architecture manufacturing. Then we'll come back to powder bed fusion lab. Okay. The ground floor you can assemble. Our research scholars will guide you where we can take you. Okay. Thank you.
What's the basic principle here? Just think. Okay?
The powders are made, wires mainly made.
Fine. Okay. Okay. So mostly, first of all, the powder will spread the substrate, right? With the help of the laser, it will go into full melt. Next, after the next layer will come. Means stacking of 2D layers. Finally, you get the 3D part. So, okay? This is a basic principle. So, this is a 3D system machine. DMP Flex 100. Direct metal printer. Flexible. 100. 100 means build volume. 100 into 100 into ATM height. So, ATM. So, laser power will be around 100 watts. So, here in this machine we can use 4 materials, different materials. Titanium, aluminum, stainless steel, followed by cobalt-rhodium. Okay. Before going to load the powder, first of all you have to do some pre-processing techniques. What is that means? Like powder. Powder is having 45 micron particle size. So in order to maintain, you have to do some sieving because suppliers will use some random particles. So in order to segregate, we have to use some sieving technique. Yeah. Why? Because to remove the oxidation, like moisture. Yeah. Yeah. Then after load the powder using glow ports instead of with the help of the glow ports, you have to load the powder in supply mixture. And followed by you have to give some fabrication pipe we used to call it. Like I think they might thought about 3D expert, right? 3D expert software
system that like a software that you need to work on it with the machine. Whatever the machine, the process parameters, everything you can give in that software.
After giving the first of all roller on the substrate. Then the laser will go into melt the powder particles. It will fill off 2 layers, 2D. Finally, you can get 3D form. So here there are 4 5 parameters. Layer thickness, has spacing, and another part you can change laser power. You can change. Yeah, has spacing in the sense like the laser will go into the powder, right? And the specified region. You have to give some spacing of the 2 lasers. Here you can observe do one thing one by one. Can observe here. I can tell you like what you understand. Yeah, first see the process, then I will show you the part. One by one.
You can see the sintering. Mannoda explain
We have to do post processing. Like what are the post processing techniques? First of all, I need to remove the component of the substrate. Vertically. Fine. Next, apart from that,
Extra.
yeah. What is the process? Like what is the technique? Sandblasting is fine. Because some particles, unmetal particles will go inside, right? For this lattice especially. How do you remove? Have you heard about ultrasonicator? Ultrasonicator, which is used to vibrate the sample. Okay, that's what we can use. Of course, sandblasting also you can use, but for these intricate shapes, like you can't use that sandblasting because the flow it won't go inside like directly because it is having curvature kind of thing. Okay. That's a problem. So better to use ultrasound indicator. So that's also one of the post processing technique. Now apart from that, okay, fine. Next. Yeah, surface grinding also you can do. And heat treatment. Okay, but in our lab we are having sandblasting followed by open furnace. Okay. In between we can show inside process.
Yeah, once it was printed, we will remove it from the build. Then the printed samples will look the same. Like whatever what you are going to give the structure, that will be depends. Here, if you can see, it was more than 45 times. This lattice, if you can see. So they have given some support here. You can, if you can visualize see it, there is some solid support, right? That will be in order to having some overhang structures. So once after this, we will be cutting with remove the sample build plate using a viridium. I hope you guys heard about it, right? There will be some wire which is of a thickness 0.18 mm. So it will through the conductivity it will remove the parts from our build plate. Best possibility to remove the build plate samples from the build plate is of viridium for additive samples, I can say, because we are very much depend about the material and everything. We don't want to get wasted. So it will be having very minute thickness which is of 0.18. So it will be considered as a negligible. In that case we will remove it. Then for normal samples, solid samples, in LPBF you can say that mostly the near net shapeable components will get obtained. But there will be still we need some more surface, I mean like a more smooth surface. Here you can see some roughness, it will be having, if you can touch it, you can get to know. There will be some higher surface roughness. In that case, there will be some post-processing techniques, you can say short pinning, sandblasting and those things. That will help you to reduce the surface roughness. Here we can see, this is the sandblasting. It was not on. This is it is also just like a glow box which you have seen it in LPBF. The sample will be kept inside and you have to hold it with using glow box only. Because you can see there will be some sand blast. You can see, right, very small parts that will be coming with some high pressure and it will hit the surface and remove the whatever the higher component are. It will make you the surface to be smoother. So if you just, there will be large reduction in the surface roughness using this sandblasting technique. And also there will be some other process, short pinning and everything that you can